Good morning and good evening, ladies and gentlemen. I am Jun-Yun Kim, a professor at Sungkyunkwan University, Korea. And I'm the moderator of the 49th KAST International Symposium. First of all, it is my great pleasure and honor to organize this symposium and to welcome all of you in this symposium. Especially, I would like to express my sincere thanks to the 7 invited speakers in this symposium. This year, we have a 49th KAST International Symposium about OLED, and last year, we also had a successful symposium. This year, the title of this symposium is "What is the limit of lifetime and color purity of OLED?" We have invited 7 world top-class invited speakers to discuss the critical issue of efficiency, color purity, and lifetime of OLED. This symposium is composed of opening ceremony, session 1, session 2, and closing. Now, let us begin the opening ceremony of the 49th KAST International Symposium. Let me invite Professor Min-Koo, President of the KAST, through video for his welcoming remarks.
On behalf of the Korean Academy of Science and Technology, I would like to express my sincere appreciation to all of you from the United States, Japan, China, and Korea who have joined us KAST International Symposium entitled "What is the Limit of the Lifetime and the Color Purity of OLED?" OLED display is a key technology in TV and the cell phone. Many scientists and engineers all over the world are waiting for today's symposium. I would like to express my special thanks Professor Jun-Yun Kim, the organizer of the symposium, for his great effort. Koreans celebrate Chuseok holiday, that the Korean Thanksgiving holiday, this week, and most of the company and the public institute, including the KAST, is holiday. Let's give a big hand to our staff and the Korean participants. As you may know, Professor Jun-Yun Kim successfully organized symposium entitled "Future Direction of Blue OLED Technology" last October. The symposium was extremely successful, and we asked Professor Lee, please organize the conference one more this time. I'd like to appreciate Professor Forrest and Adachi. Both of them joined not only today, but also last October symposium. Even though we can afford to meet and discuss with each other in person due to the pandemic, I'm confident that the online symposium will be a meaningful platform for us to share benefit of our time. Thank you again.
Thank you, Professor Han, for your insightful remarks. This brings us to the end of the opening ceremony. Now, we will start the symposium with session 1. I will also chairing the session as well, and also we will have a Q&A session after each presentation. Audiences can leave questions on the YouTube if you have any question about the presentation. Now, I will introduce the first speaker, and first speaker is very famous, Professor Steve Forrest, and as you know, he is the father of phosphorescent OLED. And he will give a talk about progress in understanding PHOLED for lighting and displays. Let's welcome Professor Steve Forrest.
Let's see. First, I would like to extend my sincere thank you to Professor Lee for inviting me again. And it's with the same amount of disappointment, maybe more, that I had last year that I cannot be with my friends in Korea at this time. But nevertheless, this is a great symposium and it's an important topic. Today, I'm going to talk about a problem that I have actually been working on for more years than I care to count, and that is to achieve long lifetime and high efficiencies from blue phosphorescent OLEDs. I have some modest review, and then I want to talk about new areas that we have gone into. But I want to start off, since this is the first talk of the symposium, to just remind people that there's so much yet to be done in OLED displays and lighting. It would seem to an outsider that it is very mature technology, but it is really far from it. There are significant problems still and challenges to overcome. Just some big picture issues. I think the first is a bullet that I've had forever, but it's becoming less and less meaningful. Materials, all displays today are made with small molecule, vacuum deposited or vapor deposited small molecules. And that's really because of the ease of their processing and the fact that you can achieve very high purity. And I can never overemphasize the importance of purity in organics. It is the same challenge that you'll face in inorganics. If you have impure materials, you will not achieve the high performance, and you'll certainly not achieve the lifetimes that you could do otherwise. I'm going to talk a little bit today about getting the light out, because it really comes into the lifetime. But really the emphasis of the talk is how to get long blue lifetime. And I'm going to talk at some length about both heavy metal complexes as well as TADF materials. And I won't talk about these other areas, but I just want to remind people that patterning still remains a huge challenge for getting the cost down in displays. So a couple of years ago, I wrote a book on organic electronics, and in my first chapter, I talk about the myths surrounding organics. And one of the myths that has been around since the beginning of organics is that organic devices really don't have sufficient lifetime to be useful. And so I put together this chart just to give you an idea that the lifetimes can be quite long. As a matter of fact, we have published two papers, one as late as this week, on organic solar cells. The small molecule solar cells we published about a year ago showed extrapolated lifetimes of 27,000 years, which always makes me smile a little bit, because I know that I will be retired before anybody proves me wrong. But more recently, the high efficiency cells based on non-fullerene acceptors, also their combinations of small molecules and polymers, have extrapolated lifetimes of 30 years, which is really quite good for any solar industry. These just show, this chart is always a little bit outdated and never quite accurate, because nobody's really going to share industrial grade, really high quality material characteristics. So this is just pulled off the web or the literature, etc. But you can see that with the exception of blue, the lifetimes are very good for these OLEDs based on phosphorescent emitters. Again, this is probably a bit outdated. I just pulled this from my book. But the TADF molecules still are well behind in their maturity. We'll probably hear more about some more updates on that today. But you know, if you've been working a long time on a problem, you tend to solve it slowly but surely. So that's why the metal complexes are doing well. Okay, so let me keep going. And one of the things I'm going to do is I'm going to light up my laser pointer. So just as a bit of review, I think this is something that everybody knows, that the lifetimes of reds in general are better than greens, in general are much better than blues. And this, of course, the implication becomes that device death is energy driven. It wouldn't seem, and I've been asked this question many times, that the blue exciton of 2.9 eV isn't really much larger than that of green, but green we know lives forever. I just showed you a chart where it shows it's about a 1,000,000-hour lifetime for the T50 and probably hundreds of thousands of hours for T95. And blues are just, they're really down, way, way down from there. But these are exponentially driven processes. There are bonds within these various molecules that can shatter, can cleave when there's a lot of energy, and you land an exciton on one of these molecules and they cleave. But what's important is that according to a model that we've been talking about for a long time, we developed it in 2008, my student Chris Giebing, which took a long time to gain a foothold, but I think people are now, everybody agrees that this is the route to blue death. And it's because it's due to triplet polaron annihilation and perhaps triplet annihilation. And what happens is that in one molecule, as you de-excite it, it delivers its energy to an adjacent dopant, and that is now at twice the energy. So we're at 6 eV, very easy to break a bond. Of course, not all of the energy that is delivered here will end up localized on a bond, so it is a fairly rare event. But when you have hundreds of millions of exciton radiative processes per second to deliver the light that you want, even a rare event will end up destroying molecules. So this was the model we came up with. It was a purely physics-based model. But I want to now talk about the main implication of that model, and because that then gives you the roadmap to making blue PHOLEDs, and I would also say TADF molecules. Again, I'll talk about those in a bit. It gives you a roadmap to perhaps, I'm not sure, but perhaps to the solution. All of the models, all of the routes that we have developed and understand require reducing the triplet density. So this was one of the outcomes of the model, which is the probability that triplet annihilation will result in molecular bond dissociation, so destruction of a molecule, is, forget about the numerical factors here, they're of no significance. But if you have a defect formation rate, that is, after X number of excitons land on a molecule, there is a breaking of a bond, that's the defect formation rate. Most importantly is the radiative lifetime of the triplet, and that's the radiative rate. This is just the radius of the molecule. So if you want to reduce the destruction rate, or the probability that triplet annihilation will result in the molecular bond dissociation, it's pretty clear that you just have to reduce the number of triplets. But that's not very useful because you need a certain amount of light out. So what you do is you reduce their density. And the way you can reduce their density is you can reduce the triplet lifetime. So that's lever number one. You can enlarge the recombination zone. By the way, we've tried all of these things. And then you can increase the outcoupling efficiency, something that doesn't get talked about much. But the more exciton, or the more light you can get out of the device, the less hard you have to push it. So this is the roadmap to reducing in metal complexes the emission decay time. And interestingly, the first really efficient, lovely device we ever built was built using ERPI as the emitter, and it turns out that its emission decay time, its phosphorescent decay time, is 1 microsecond, and it's about as short as it gets. You'll notice there's an asymptote to this curve. This beautiful collection of data was developed by Yeob in 2011, and it still holds today. Now, the key to all of this is, you'll notice the horizontal axis is the zero field splitting energy. And if you look at the triplet level, it has 3 sublevels. Their spin states are 1, plus or minus 1, and 0. And when you have coupling to the metal center of the molecule, you get spin orbit coupling, and that lifts the degeneracy, and you have these 3 substates. And the smaller you can separate these substates, the faster the emission rate, because what happens is that if I excite into E1, I need to thermally get it, let's say, boosted up to E3 if that's the fast emission time. So by collapsing these levels and lifting that and reducing the energy splitting, then you can make sure that the triplet is more rapidly emissive, it becomes more efficient, and you therefore also reduce the density of triplets to get the same amount of light out in the EML. It just turns out that metal ligand charge transfer is much more effective than ligand-centered molecules to produce a short triplet lifetime. And this means that you want to go to pseudo-octahedral rather than dihedral molecules. Lifetimes of around 800 microseconds have now been achieved in the blue-green with iridium-based carbines. This is work out of the Thomson group. And this just gives some examples, and we're very much wedded to the meridional form of PMP, as you'll see. So let me now talk about things. Again, I've talked about this before, but we're going to go somewhere in a minute with all of this. But I just want to go through how do we reduce the density of triplets. And one solution was to increase the emission rate by putting in a third dopant molecule, which we call, or a third molecule into the EML, a second dopant called a manager molecule. And what happens is, usually we like to have that type of transition and we get our blue light out. But sometimes we have this double, basically Auger process, which leads to a molecular dissociation. Here you just see that we're losing 50% of the emission intensity or efficiency. But of course, you can also cause this dissociation reaction. By putting a manager molecule in, the hope is to make this transfer over to the manager, and that will then transfer back, or the manager molecule will be the sacrificial element in the EML. And we demonstrated this back in 2017. Intermediate energy, the requirements for the manager, it must have an intermediate energy between the hot state, which is the T star, and the lowest triplet. It ought to be stable. You don't want to destroy all these things really fast. And there has to be very fast energy transfer. It turns out this is extremely hard to make happen. The molecules are few and far between at these energies. We used an iridium carbine for the manager molecule. We doped it into the, and here it is. ERDMP, by the way, is the most stable blue, and it's a bit of a blue-green emitter that we have been able to come across that's a published molecule. I can't tell you what is going on behind the scenes in companies. I'm sure they've come a long way, but I'm not privy to that material, information. But these are carbines. They're the iridium coordinates with a carbon with a lone pair. We've doped this manager at various locations within the EML. You'll notice that the dopant itself is graded. I'll talk very briefly about that in a minute. And when you do this and place the manager molecule in that sort of center location, the LT90 goes up 3 times or 5 times from just a conventional OLED, and 3 times up from a graded OLED. Again, I'll talk just very briefly about grading in a minute. So it helps, but number one, manufacturers barely like to put 2 molecules into an EML, let alone 3. And I've already mentioned that finding the right managers that are stable is just as hard as finding the right dopants that are stable. We're talking about a series of molecules when you're in the blue, where the LUMO is very close to the vacuum level. And when it's very close to the vacuum level, it can be easily reduced or it can be easily oxidized because the HOMO is destabilized as well. So, and then of course you have to put this into a host, which has to have perhaps even higher LUMO. And so the materials challenge just gets multiplied more and more. We're talking about LUMO energies, which are only maybe 1 to 1.5 volts below the vacuum level. So these are rather unstable molecules to begin with. So materials, although I've talked a lot in the past about physics, the materials I really want to emphasize in this talk still remain a major weak point. There are both physical defects being formed, but also the materials, and I'll talk about that. So spreading out the distribution, everybody knows about this. You can stack OLEDs. This is a way of also increasing the output efficiency of these things, but this is UDC work. A 2-unit OLED has a 13,000, these are white OLEDs, 13,000 hour LT70 versus a single unit OLED. All we're doing really is demanding 50% as many photons per element than you do in a single element device. The one thing that we did, I think, that made the biggest splash in my lab, and perhaps elsewhere, is, again, we're just trying to spread out the emission zone. And to do that, we started to grade the emission zone because all iridium dopants carry holes. And the host, such as CVP, generally carries electrons. So the formation of the exciton itself is always by charge trafficking, never by energy transfer. And this is true of all iridium dopants. And I think most platinum-based dopants as well, because you first start by injecting the hole, then you inject the electron, they then trap onto the emissive molecule, and out comes the light. Now, it turns out that the dopant mobility, hole mobility, is always much higher than the electron host mobility. So the idea that we had was, why don't we taper the dopant density down from the HTL to the ETL, so that we basically create a bottleneck where the holes sit in the center rather than, if you do a conventional OLED, they sit right at the edge. And this was what the exciton density looks like in this case. And we did that. And this was the first significant increase in blue lifetime since 2000, when they were first introduced. I believe that Chihaya was in my lab and was one of the people who first developed the blue PHOLED device. But they've always been the weak link in the whole system, and they've been sitting at T80s of, well, 50 hours for ERP DMP, and that's a really good blue. But if you grade and you stack these things, you get up to 10 times the lifetime. And I think in the published literature, this is still about as good as it gets, but it's still not good enough for lighting and displays. And this is not a pure blue, a deep blue for displays. At any rate, we, a couple of years ago, we also demonstrated a very nice white device. It had, I think, a stack of 4 red-green sections and a blue section that had both managers and a graded EML. I don't want to go through all this. I'd probably get confused as you would, as if I described all the layers that went into this. It was done by my student Caleb Coburn, who's now, not surprisingly, at Apple. And you get very high luminance out of these things, a great correlated color temperature of about 2800 Kelvin, a CRI of very close to 90. And when we ran this thing, the T70, which is the lighting requirement of the Department of Energy, is about 80,000 hours. And that's a fully phosphorescent device, very efficient. And the T70 at 3,000 nits goes down to about 14,000 hours. What you notice is that the color temperature drops. That means with aging, which means that it's shifting to the red, which means that it's the blue that's wearing out, as we would expect. That's good enough for lighting. It's far from good enough for displays. We then started to get really nervous about what we were doing and thinking maybe there are other things that are wearing out, not just the EML constituents. And so we started to put these sensor layers, put phosphorescent dopants on both the ETL and the HTL side of the blue OLED, and we put a fluorescent dopant on the ETL side to see if there was leakage of these excitons into the surrounding layers that was actually leading to the decrease in the emission from the EML. If the thing is leaky, it's not going to hold the excitation in the right spot. And this just shows the accelerated decrease in the emission from the OLED, and this shows the either decrease or increase of the emission from these peripheral regions. And you can see the changes are really tiny. And we came to the conclusion that it's all in the EML. Charge balance and exciton leakage are responsible for less than 3% of device degradation over time. And you can see the excitons don't change at all. The singlet exciton leakage doesn't change at all. I think one of the most important thing we did was a year and a half ago, where we moved away from physics and started to ask what is the chemical origin of the degradation. And this is where things got very interesting. We used time-of-flight mass spectrometry to look at devices after aging. And what you find, these are really stable blue iridium DMP devices. We aged them down to, I think I saw it here, T40. And you can see there are fragments that exist in the aged versus the unaged device. We wanted to know, was it the dopant or was it the host? So you just look at the mass spectrum and you get all these lines coming out, and dopants we label as a D, ETL as an E, and an HTL as an H, I guess, as our signification of the molecules we're looking at. And you can see that we see all these fragments, which are the red bits, and there's two routes to destruction of the dopant. It's either ligand loss or ligand rupture. It turns out that the fragment peak height from ligand loss is an order of magnitude higher than from ligand rupture. Ligand rupture just kind of pulls out bits from the ligands themselves. And then working with the Thomson group, we then looked at all of these fragments. Again, the H's are for the, I guess that's the host. Yeah, that's the host. D is for dopant. And so we have all these fragments from the host and from the dopant. And you'll notice that some of these fragments, this is, by the way, the HOMO and LUMO of the host and the dopant. So this is kind of the boundary where the action is electronically. And you can see a lot of these fragments, their levels are well outside of this, the energy gap. And then some are above it and some are below it. These are just filled with electrons. These are just filled with holes, so nobody cares. But you'll notice there are several in here that are mid-gap states, and this is where these are the fragments that are killing the luminescence. And it's from the host and from the dopants. So we have clearly identified what is causing the death. Fixing it's another matter. So now I want to shift gears entirely and address the thing about TADF. Now, most TADF molecules are rather slow, so that's going to be a problem because you have a very high density of excitons when you have a slow emission. But Mark Thompson has worked on these classes of TADF molecules that use metal linkers. As a matter of fact, he's completely focused on what he calls coinage metal linkers. Coinage metals are copper, silver, and gold. And with these linkers, we get very good separation of the LUMO and the HOMO. These are just two compounds. They're both carbines, copper carbines. One has a oxygen on both sides of this acetate group, and one has oxygen only on one side. The copper, they're carbazole-based compounds, have very fast emission from 1 to 10 to the 5th inverse seconds. With the silvers, we're getting right now about 3 times, about 30 times 10 to the 5th inverse second, which comes out to about 300 nanoseconds. So the silvers look very, very promising as well. But these are the coppers. They tend to be the most stable. One of the outcomes of this was really wonderful. It was so good that I had to put it in the book, because here he's made a series of compounds. They're just listed back here. You can see they're 1, 2, 3, 4, 5, 6. And you can see they're emitting from the very deep blue to the, well into the near infrared. But what's really lovely about this, because I'm a physicist, is this falls on a line. This is the non-radiative rate, recombination rate, and you can see this exponential curve, which is a beautiful demonstration of the energy gap law. And you just love to see things like that. Compound 1 doesn't quite fit on the curve because with its high energy, there are other mechanisms for, it's not a single mechanism for a non-radiative recombination. But from this, you can see what you can, without going through this is just a kinetic equation. If you look at the lifetime as a function of temperature, you get this nice S-curve, and that allows you to resolve all the zero field splitting aspects of this material. But the TADF lifetime is only 1.3 microseconds. Again, this is about 4 or 5 times longer than some of the silver compounds. Stuff looks great. We put it in a device. We made devices with 20% efficiency without any outcoupling. The compounds have high efficiency and short lifetimes, but the materials themselves are unstable. So they don't last nearly as long as even the blue metal complexes. So the last thing I'll talk about is increased outcoupling, and there's been a lot of talk. I think J.J. Kim is really one of the experts on this, but we have been quite puzzled by what creates alignment. And we have a series of, in this case, platinum compounds. We've also done this with iridium compounds. But we basically have this model where you have an ancillary ligand and you have a chromophoric ligand. And if the van der Waals attachment, or the orbital scale of the ancillary ligand, is much larger than that of the chromophore, then the ancillary ligand is going to stick down to the surface, and that will have the host in it. Vice versa, it'll still create a vertical alignment if A is less than C. Now, if A is equal to C, they're going to want to just lie flat because they're going to van der Waals attach to the organic surface as they fall down in vacuum. But that's only if A is equal to C, which is large. If it's a small ligand, then the alignment will be random. The reason I want to talk about this, of course, is because the more light we can get out of this thing, the less we have to work the chromophores. Now, what you want is to have horizontal transition dipole moment, because that will allow you to, all of the emission then will be perpendicular to the substrate, which is then the maximum for harvesting the photons. In this condition, of course, you're radiating in plane, and then it's very difficult to capture those photons. So if we add aromatic rings, we should get a higher host interaction, which means we should get a horizontal orientation, which means we should get better outcoupling. So this just shows a series of molecules. These are platinum complexes with this ancillary ligand here. And this shows the transition dipole moment. It might be, yeah, this transition dipole moment. But here's, this is the ground state dipole moment. It shows it to be highly in plane. Now, this is the theta horizontal, is the horizontal alignment percentage. What percentage of molecules are actually horizontally aligned? If 67% are horizontally aligned, because you can align along the x or the y axis, then it's random. And then you get one on the z axis. So this one shows good vertical alignment, because we have a very strong, very large aromatic ring structure on the ancillary, in this case, the chromophoric ligand. In this case, it's a very small dipole moment, and you can see it's very close to random. And then on this one, we have extended the this naphtho group basically we place here, and this gives us good horizontal alignment. There's essentially equal pi system attachment for the aromatic to the chromophoric. And we talked about this in advanced materials. More recently, we have done this with iridium ligands with very much the same result. So last thing, this is the last thing I want to talk about, because this is becoming a hot area. It's using cavities to increase lifetime. Now, cavities have two good effects. One is they can shift these long green tails and push them into the blue and make your chromophore bluer. Here, this is some results out of Universal Display Corporation and CCNY, where they have used plasmonic coupling to the top contact of a semi-transparent top-emitting OLED. Here they're using ERPI as the chromophore, as the phosphor, and they have these little silver nanodots scattered along the top. And this allows for plasmonic coupling. What does plasmonic coupling do? It decreases the radiative lifetime, again, reducing the density of excitons in the EML. So we excite surface plasma polariton modes, and that increases the Purcell factor. The Purcell factor is just basically the cavity strength in many respects. So the lifetime in the cavity is the natural lifetime divided by the Purcell factor. And here you can see there's about a 2 times increase in the decay rate, which means the Purcell factor is around 2. So now we've made this 2 times higher. That should lead to a longer lifetime. Unfortunately, ERPI lives long on its own right, but even so, you can see they really turn on the current here, and the plasmonic device shows a twice as long a lifetime due to the Purcell factor as the non-plasmonic device. And again, you go back to this. This is from the analysis that I showed in the beginning, and it's following that just perfectly. Unfortunately, you also lose some of the efficiency of this thing, so it's not running as bright. And that may be because we're reducing the number of excitons in the zone. But it looks like the plasmonic approach is a good one. So to finish up, the pathway to long lifetime blue emitters is that are controlled by triplets, which is both phosphors and TADF. They're both controlled by the triplet population, remains a long and narrow path. We need better chemistry, so we still have to find better molecules. I think that Professor Lee and Adachi have really done some very nice work here, as well as obviously Mark Thompson. We need lower density exciton emission zones, shorter radiative lifetimes, improved outcoupling, and coupling to plasmons. This is still and remains the single most important challenge confronting organic electronics today. And certainly it's a big player in the success of OLED displays. Blue lifetimes appear suitable for lighting because they use lighter blues and fewer photons per segment than in displays. And then I don't want people to lose sight of the fact that there are other challenges. And this is my group, and I want to, of course, extend my thanks to the Thompson group at USC, who we've worked with for half my lifetime, I think. So thank you very much.
Okay, thank you very much, Professor Steve. Thanks for giving us insight about the blue phosphorescent OLED. Actually, I have one question about your presentation. So you mentioned the external lifetime of phosphorus, and especially you mentioned that the external lifetime of iridium phosphorus can be less than 1 microsecond. And then how about the external lifetime of PT complexes? What will be the limit of the PT complexes? Of course, field splitting is a little bit low in the PT compound, so there can be some limits. So can you comment on that?
Yeah, I can. The problem is exactly what you say. The platinum compounds are ligand-centered by and large. Not entirely, you can get some MLCT in there as well. And so their lifetimes tend to be longer, and there hasn't been a compelling story yet that I have seen anyway, and I must say that I don't know 100% of all the literature that shows that platinum complexes can live longer than iridium complexes. They all suffer from exactly the same disease, which is exciton annihilation that creates these high energy states. So whether it's TADF, platinum, or iridium, there doesn't seem to be much wiggle room there. So it's interesting that there is this, what looks from the Yersin plot, an almost fundamental limit to the how small the zero field splitting can get, somewhere around, I think 70 wave numbers or something like that. I think that is simply a factor of, with metal ligand charge transfer, you get really good coupling to the atomic center, but there's only so much coupling you can get. Maybe if you can shorten those bonds up, but these are metal carbon bonds and things like that. They are the length that they are. But if you could shorten them, you could increase the MLCT. And that's probably going to be with pseudo-octahedral type of molecules. But everybody always surprises me by doing something completely different.
Okay, thank you very much for your presentation. Okay, thank you again.
My pleasure. Thank you.
Okay, we will move on to the next presentation. Next speaker is Dr. Sun-Ok Jeon from Samsung Advanced Institute of Technology. She is the leader of blue phosphorescent OLED development team of SAIT. So her title is Blue Organic Light Emitting Diode by Metal Complex Emitters. Let's welcome Dr. Sun-Ok Jeon.
Thank you. Thank you for kind introduction, Professor Lee. Can you check my files? Yeah. And thank you for inviting me this honorable event. And this is Dr. Sun-Ok Jeon from the site at Samsung Electronics. And today I'm going to talk about the blue organic light emitting diodes by metal complex emitters. And this is my contents of my talk, and I will give you the briefly review this history of blue OLEDs and the research development of the research at sites. Then give you a little background about the blue metal complex materials. And I will explain the contents related to development of the phosphorescent materials, both iridium and the PT complex, its part. And actually, people who are watching and presenting today know this OLED history and the mechanism very well. So I will skip the detailed explanation. But however, we all agree that the most important thing in the OLED industry is blue. So that's why we are here to discuss lifetime and color purity of the OLED. So I can say, in other words, the display efficiency significantly depends on the blue emitter systems. And many papers reported the phosphorescence and TADF and hyper system to get high efficiency because these systems utilizing the triplex tone, so it is possible to enhance the efficiency. So in this talk, I will focus on the blue OLEDs by the metal complex emitters. And this is the discovery timeline for the OLED development of sites. And we started the polymer OLEDs in 1998, so it has been researched over 20 years. In 2008, Samsung Electronics and Samsung Display unified the OLED research group and Samsung Mobile Display to produce the mobile display. And it was successfully applied the many materials to mass production of the Galaxy series. And site focused on the green hosts and the blue dopant from 2012. Actually, I joined the company in 2013. So since then, I have been continuing research on the blue emitter until now. And to simply tell you about the result of the blue dopants, and this is our result. And this is the current state of our result. And in the EQE graph, and phosphorescence using the triplex tone has a high efficiency, more than 1.5 times compared to the fluorescence. However, because of the longer decay time by triplex tone, the lifetime is shorter than the fluorescence. I can't share more data, but we've got the major progress in the blue OLEDs. And there are two types of metal complex materials. And one is the octahedral iridium complex with strong MSD character. So it is short decay time and less segregation. However, the blue emitter consists polar unit, so it causes stability issues to make the chemical degradation, and it is also hard to design the blue emitters than red green emitters because of the photosynthetic yield and the isomer issues. And the other one is the scale planar PT complex. And compared to the iridium complex, it becomes better device performance for the blue by narrow banded spectra and lifetime by stable tetradentate redundant structure. In addition, when we adapted strong electro-withdrawing group can realize the deep homo energy level to reduce the hole trap in the devices. However, the PD dopant has weak MST emission, so it shows the longer decay time than iridium complexes. And let's talk about these two types of phosphorescence OLED study in detail. So in this part one, I will give you the iridium complexes with the following the information about the emission dipole orientation and titration effect. And we published the paper about these topics in Advanced Optical Materials, and here are the cover pictures. And the blue iridium dopant material actually developed heteroleptic materials, so it's difficult to achieve the deep blue color with a long operational lifetime. So homoleptic materials were developed to the device performance blue. It is quite difficult to improve the efficiency due to the intrinsic properties. So in order to solve this problem, we manage the transition dipole moment, and we synthesize the homoleptic iridium complex and design in the direction of the increasing the orientation of the ligand. So here are the chemical structure. And as you can see, there UV pair curves, all the complexes show strong absorption band at the region over here, and which can be assigned to allow the pi star transition of the Rigan. And we also can find out the broadband at around here is a mixture of the MLCT transitions. And although the 1 to the 5 structure have a similar backbone, the pairs slightly move to a lower energy by enlarging the conjugation extension through the adapting bulky units from the metal to the biphenyl. And when we see the T1 optimized structure from the D5 in here, the orange arrow directions indicated the transition diaphragm movement. So when we attach the substituents in this direction, it may increase its orientation from 79% to 91%. So to investigate the orientation ordering of the dopant materials, we performed MD calculation to find theoretical atomic model of the emission layer. So if you look at this figure, the MD calculation was performed to simulate the actual deposition process. So the deposition process was simulated by dropping the dopant one by one. So this green one is dopant material to the host matrix. So the orientation of all dopants comprising the morphology are analyzed. So experimental dipole orientation is calculated by this equation, and black dot shows the experimental values, each iridium complexes, and the blue letters means are the orientation calculated from the simulated morphology. So it was well matched, and also the preventing of the aggregation by the introduction bulky structure effect of the increasing the dipole orientation as well. So this is the energy level diagram of the device structure, and there are the materials we use. And this is the bottom OLED device result, and we fabricated the 5 different iridium complexes in the 10 weight% doping concentration. And the condition of the actual champion device data, which is the 5 dopant, with highly Burkini substituents with high EQE of 26.3%, and the lifetime of 169 hours 8080. And it has a great improvement of the device performance in the D5 devices is due to the large orientation, which is 91%. So as the material was improved by the increasing the orientation of the synthesized iridium complex, we were attempted to improve the lifetime, enhancing the dopant stability by replacing CH bond to CH bonds of the benzylic position to the CD bonds. So among the previously synthesized material, we chose D4 here. So we confirmed the degree of the deterioration iridium complex by high resolution HCMS and the NMR spectroscopy. And as shown here, the substitution rates at each bonds are 91%, 81%, and 67% respectively. Also, they compare these two dopants of the photophysical properties were the same. So we expected the EQA will be the same data as well. And as we know, the benzylic position is very weak. So we calculated bond dissociation energy by DFT calculation. So we find out this third position was the weakest at 30.5 kilocalorie per mole. However, the bond dissociation energy value is larger than we expected, so degradation may not occur. But it happens anyway. So we studied that the reason for the degradation in the emission layer by DFT calculations. So we thought the interaction with the host materials can be accelerate the reactivity with the benzyl position of the metal complex emitter. Actually, most of the host materials that consist of the carbazole moiety. So when we calculated the reaction path, delta ZP is 0.74 kilocalorie per mole, which is easily reacted in the emission layer. So in other words, CH bond triggers the chemical decomposition of the device with the cationic phenylcarbazole. So as you can see, the transition state structure here, the ligand, this is the bigger model of the transition state structure, and the length of the CH bond and the NH bond being 1.52 angstrom and 1.19 angstrom. So we believe that the optimal structure of the transition state after hydrogen obstruction reaction can realize in the emission layer because of the result of its bond length. And this is device performances, and we evaluated the effect of the deterioration OLED device was fabricated as follow the device energy diagram that I showed the previous page. And it is the optimized device performance and 1.58% doping concentration. And as we intended, the EQE values of the between D4 and deteriorated D4 are almost identical. But the device lifetimes are dramatically enhanced by deterioration. And deteriorated D4, the best device performances measured to data with the max EQE 25%, and device lifetime is about this. And all the device properties summarized in here in this table. And also in the published paper, we synthesized the other deteriorated iridium complexes as well. And it shows exactly the same trends that I explained here. Yeah, and let's move on to the part 2. So I will talk about the PT sensitized, the hyper deep blue OLEDs. Actually, there are not many papers on the development of the blue PT complex materials. And Jeon group continued to study the tetradentate metal complex using the platinum and the palladium. And also they studied the efficient diffuse blue tetradentate PT complex with narrow spectral bandwidth, and it shows 20 nanometers from the PT ON7 DTB materials. However, but the lifetime of the deep blue phosphorescence remains insufficient to produce the mass production. So practical use in display and lighting application, the hyperfluorescence OLEDs has been proposed to achieve lifetime and efficiency at the same time for deep blue. So there are two types of hyperfluorescence system. But I'm going to introduce the metal complex sensitized one, for example. So in this reference paper, it was used the iridium complex material as a sensitizer here for hyper OLEDs, and the result of the device have been increased lifetime up to 493 hours with a white color coordinate is 0.086, and it is quite really good device database. And we studied the blue, the hyper OLEDs that incorporate the square fluent PT complex as a sensitizer, and we chose the PT ON7 DTB, and the most conventional process materials and the MR type materials as a terminal emitter in the emission layer. And there are three important key requirements to get high efficiency and long lifetime at the same time for the blue OLEDs. And I'm going to explain what it is and how to solve the problems to get high performance of the deep blue devices using this PT complex as a sensitizer. And firstly, it is we need to suppress the exchange of chip fraction through the dextrose transfer. So in the case of the conventional fluorescence emitter materials, the dextrose energy transfer prevented by the testing the TADF group like here. In the case of the MR type the materials, the separated sensitizer to this emitter material, this time using a dimer structure like this mu Darner to satisfy the first conditions. And secondly, it is important to maximize the spectral overlap. So as you can see the graph here, we find large spectral gap between the PL of the PT complex and the absorption of the finer emitters. And finally, so it was necessary to the alignment of molecular orbital levels for 3 emissions materials. So to cut off the direct external formation by charge trapping on the finer emitters. So it looks so when we see the energy level of those emission materials, it looks effectively reduced charge trapping on the emitters. And therefore, the sensitizer effectively the moderate direct charge trapping on the emitter. And as we put the HOD and EOD devices in these figures, and the figure shows leading to the dominant trap state recombination and resultant external formation of the sensitizer. And as you can see this diagram, the biggest difference in the T1 energy level between the TB-PDP and UW as of the finer emitters. So based on this, emission mechanism is also a little bit different, and let's move on to the next page to explain that. And as you can see here, this is the only differences in the energy transfer process. In the TB-PDP hyper OLED, it is essential that the faster energy transfer from the sensitizer to TB-PDP be efficient for the harvesting triplet stones for the emission due to the low triplet energy of the TB-PDP. On the other hand, in the new Dobner hyper OLED system, through the even though the textile energy transfer occurs between the sensitizer and the emitter, the new Dobner, which also is a TADF material, so can convert triplet into the single extron through the reverse intersystem crossing. So from the the OLED mechanism, as I mentioned before, then we investigated the photophysical characteristic of the device by transient PR. And this is the condition of the doped film. And PT complex act as only sensitizer that proves external decay time. And the external decay time is the decay time of the PT complex is 3.3 microsec, and it was confirmed that the decay time decreased as the doping concentration increased. And as I mentioned in the iridium part, it shows the high EQE in the bulky iridium complex device due to the large orientation. So it is possible to enhance the device performance due to this result. So PAQI and the orientation of these two finer emitters are much higher than those of the PT complex. And also its radiative decay rate is here. And it is increased decay rate when it doped fluorescence dopant film. So we fabricated this condition to make a device. And this is the device performance of the bottom emitting OLED. And as I mentioned, this is the optimized device conditions. And So looking at the EQE graph in the case of new Dobner with a large orientation in here, so it becomes the efficiency tends to be high. In addition, as the energy transfer is very smoothly transferred to the terminal emitter. As you can see, there is no double emission spectra. And compared to the single PT device, the lifetime was much longer than those of two devices. And I summarized the data in this table below. Actually, to further demonstrate the feasibility of our proposed device for actimetric display application, so we fabricated a top emission hyper OLED. So this is the optimized device performance at the 1.58% doping concentration in here. Top emission OLED shows the narrow half is narrowband spectrum than the bottom OLED due to the microcavity effects. And as a result, deep blue emission was obtained with the white color coordinate of 0.13 and 0.09 respectively. And EQE was actually the same trends as I explained the previous page in the bottom OLED devices. And it was confirmed the lifetime was also much higher than that of the simple phosphorescent PT device. And the best result was originally obtained from the new Davna device with a narrow band spectrum, and it shows the color conversion efficiency is over 400 candela per ampere with the over a lifetime is over 254 hours LT50. So I will summarize of my talk. So we talked about the result of the two types of metal complex materials. So in the first part, we find out the orientation and duration effect of a homoleptic iridium complex by simulation to enhance the device performance. So we got the high EQE and the long lifetime, but it's still insufficient both for the color. And in the part 2, we minimize the external lifetime using the fluorescence materials as a final emitter in PT sensitized system with narrow band spectra. So we've got the high quality of device performance for deep blue OLEDs, and LT50 is over 259 hours, and also the white color coordinate is 0.09. Yeah, thank you for listening my presentation. Thank you.
Okay, thank you for your excellent presentation, and we have some question about your presentation. Actually, you mentioned like some PT sensitized fluorescent devices. So we can use PT or iridium complexes as the sensitizing material for the fluorescent emitter. So then what will be the merit and demerit of each sensitizer, like a PT and iridium? Can you comment on that?
Actually, the PT is more, we prefer to the maker deep blue color. So, but actually the iridium has the broadband spectrum, and also they have also the vibration peak is very large. So it's not for the good to the mass production. So actually we prefer to make a PT sensitizer to the mass production because of the narrow banded spectrum. But actually I'm not sure what is the good or not good.
Okay, thank you for your comment. Okay, thanks for your presentation.
JY, can I ask a question?
Oh, yeah.
Okay, thanks very much for your lovely presentation. One question I would have is if you're using a sensitizer to a blue fluorophore, the sensitizer has to have a much higher energy because it's always a exothermic process. So how does that impact the lifetime? Because already we're worried about just getting blues to have a long lifetime. Now we have to have ultraviolet emitters to have even a longer lifetime. So can you comment on that?
Actually, we are working on that kind of a study in our company, but unfortunately, actually, I can't say exactly, I can't say that because it's kind of the confidential for the company, so.
Yeah, well, I was asking sort of a general physics question.
Okay.
Which, you know, if you have a blue phosphor, you have a triplet state, and we know that destroys the molecule because of these annihilation processes. So if I go to a hyperfluorescent type of device, and I want to have a blue fluorophore, I need a triplet emitter that is even bluer. So it's even more vulnerable to decay. So it will last even shorter than if I just made the blue device all with that phosphorescent emitter. Do you follow that logic?
Sorry, I couldn't follow it. It was a...
Okay,
I'm
well,
sorry.
I'll leave it at that then.
Okay.
It's maybe at some other time I can ask, but thank you.
Oh,
Yes, I
sorry
think
about that. Thank you.
about that, I think the key is to develop some fluorophores with very small Schutox shift. I think that is the key because as you mentioned, like of course the exosonic for exosonic energy transport, the emission energy of the phosphor should be high. That's true. So then we have to minimize that. So then maybe we can maybe achieve a good device lifetime if we have some good fluorophores with very small Stokes shift. I think that will be very important. I think.
Yeah, thank you, JY. That's helpful.
Okay, thank you very much for your presentation, Dr. Sunok Jeon. We will move on to the next presentation. Next speaker is Professor Chihaya Adachi, and of course, he is the pioneer of the TADF OLED, and his title is Recent Progress on Hyperfluorescence OLED. Let's welcome Professor Adachi.
Yeah, thank you very much, JY, for your kind introduction. And I really appreciate for the invitation of this symposium. And yeah, I'd like to talk about some of the updates of our TADF and hyperfluorescence OLED. So since we reported in 2012 the very efficient TADF in the Nature paper, harvesting triplet as the delayed fluorescence. So this works very well in OLED processes. So here you can see actually after our report, maybe I don't know how many materials, but more than a few thousand new TADF material has been developed. And this shows the relationship with the risk rate and the SD gap. So we can understand the smaller the delta ST, we can accelerate the reverse intersystem crossing rate. So as Steve said, the fast, the quick risk rate is quite important to get the stable OLED, in fact. But here is almost 80 plots of the TADF materials, and you can see even with the same SD gap, we have a, okay, in this case, 100 times different risk rate. Also, even with the same risk rate, tens of fifths, the SD gap is quite different. So we should try to understand what's happened the up conversion mechanism at first. Okay, so this is the actually okay, the Steve's picture. So we have a singlet and a triplet, and so triplet state is always longer than the singlet state because of the prohibited process. So the triplet, so because of the very long transient lifetime, excited state lifetime of the triplet, microsecond to the millisecond. So triplet has a chance TTA or triplet polaron annihilation that generate hot excited states. So the hot exciton has the very high energy, such as 5 electron volt. So the the chemical bond, for example, the weakest chemical bond is CN bond. CN bond has the bond dissociation energy of the 3.5. So the 5 electron volt is enough to dissociate CN bond. So so we should escape TTA or TPA. So we should quickly upconvert triplet into single states or decay to the non-radiatory. But for the TADF, we should focus on the first risk process. So actually, so risk rate is already well established in the 1960s by Professor Mustafa El-Said. This is very famous rule, El-Said rule. So El-Said rule tells us risk rate is given by this formula. Of course, one factor is the exponential factor, Boltzmann factor. So the smaller the delta ST, we can accelerate risk rate. And simultaneously, we have a prefactor. So prefactor is composed of this equation. This tells us, so spin orbit coupling is the very important factors. So we have to increase the spin orbit coupling to promote triplet into singlet. So of course, the simplest way is just put in heavy atoms into molecules. So TADF, most of the TADF is the pure aromatics, having no heavy metals. Even in we don't need halogens. Even with the pure aromatics, we can in fact accelerate upconvert triplet into singlet very efficiently. So what's happened? This is given by LSA group. So Mustafa described actually if the singlet and the triplet has the same wave function such as CT-CT, so the spin upconversion is prohibited. So SOC becomes 0. On the other hand, okay, let's assume singlet is CT, triplet is LE. In this case, wave function is different. In this case, we can have large SOC values. So we can understand. So we should put the different wave function between singlet and triplet that promotes the efficient upconversion. I mean, we can make a larger prefactors. So so this can be well understand this picture. So TADF molecule is the kind of the CT materials because of the TADF contain donor and acceptor unit. So we have basically CT and LE states. So CT originates from a donor acceptor charge transfer. LE localized electronic states at the donor or acceptor part. So here, okay, let's look at our picture. So singlet is CT and a triplet CT. So between triplet CT and a singlet CT is basically prohibited. So spin orbit coupling becomes very small. On the other hand, if we have intermediate state, that is the T2. So if T2 is a LE character, we can summary upconvert triplet in CT3 into LE3 at first, summary. And then we can upconvert triplet into singlet. So this is the probable mechanism of upconversion. Okay, I'd like to show you the real picture of TADF materials based on quantum chemical calculation. So we collaborate with Professor Breder's group in Georgia Tech. Now he is in Arizona, and Dr. Shankar Chen. Now he is the City University of Hong Kong. Shankar carefully analyzed the electronic states of Forces Z IPN, which is the very fundamental typical TADF materials, which composed of the 4 carbazole and dicyanobenzene unit. So this is the donor acceptor complex. And so if you look at these chemical structures, the bottom 3 carbazole is very much crowded. In fact, if we have here actually we have a 3-dimensional model. 3 carbazole is very much crowded and difficult to move. But this top carbazole is rather flexible by harvesting the thermal energy. Just 12 Kaiser, this carbazole can be easily twisted. So it's quite interesting. So here you can see S1T1 gap. So green line corresponds to the S1T1 gap, and orange line corresponds to the S1T2 energy gap against the flipping angle of this carbazole. If this carbazole flipping angle is around 145 degree, so actually S1 T2 energy gap becomes 0. So S1 and T2 can align very much with the twisting. And okay, another aspect is the wave function. So here you can see S1, T1, T2 wave functions. So the hole and electron. So if you look at the S1 and T1 wave function, it's exactly very similar. So S1 and T1 wave function is very similar. On the other hand, so T2 wave function is very much different compared to the S1 and T2. So T2 wave function, shape of the wave function is completely different, S1 and T1. This is very important. So, and we can calculate SOC value. So because of the very similar wave function, so S1 or T1, SOC is pretty small, 0.06 Kaiser. On the other hand, so S1 and T2 SOC is the 0.51 Kaiser, almost 10 times large SOC value between T2 and S1. Okay, so based on these two results, we can understand the probable mechanism. Actually, by twisting this Cobzos 145, so T2 S1 can be aligned. Okay, so first we upconvert to T1 to T2 by summary upconvert, and then T2 and S1 can be aligned, and also the SOC value is quite high. So then, even without heavy metals, we can efficiently transfer the triplet into singlet states. So this is the probable mechanism based on the quantum chemical calculations. And I should mention that actually in the I said simply CT and LE, but in reality there is no clear pure CT and no pure LE states. All wave function is the mixture of the CT and LE. So S1 or T2, S1 or T1. So here you can see it's a mixture of the LE and CT. So we call this is the hybridized local resonant CT state. It's a mixed states. But anyhow, so S1 T1 is similar, but T2 is completely different. So then we can convert triplet into singlet. So based on this idea, so our members try to design a new molecules, and actually the PhD student, Jun-Yun Kim, he got a PhD, already PhD. He tried to design a new molecules to align CT and LE states, and he synthesized actually 20, maybe more than 20 new molecules, and actually he found this molecule, tetramethyl carbazole boron compound. This material shows very nice TADF, advanced TADF behaviors. So the molecular structure is quite simple. So, but please pay attention. So we put the 4 methyl group. So methyl group is a kind of donor. So 4 methyl group contribute for the very strong electron donations. And these two inside 2 methyl group induce the kind of steric hindrance, and that induce the twisting of donor and acceptors. So 2 effects. So these 2 methyl groups. So methyl group is a very simple substituent, but very effective to change the electronic structure of molecules. And in this case, it works very much. Okay, so due to time limitation, I only focus on the TM-CZPO. And this material, emission wavelength is 467, and PLQI in PPF gas host system is the 98%, so very high efficiency. And fortunately, the delayed lifetime was 750 nanoseconds. I was really excited to see this John Wilkes data because of the we tried to make a shorter transient lifetime, less than 1 microsecond, but many TADF material show the delayed lifetime longer than 1 microsecond. So this was the very first shortest lifetime in one year ago, 750 nanoseconds. I really excited this result. Okay, and we carefully look at the activation energy of forward and risk rate, and it's interesting. Even in S1 to P1, we have a very small energy barrier, 3 millielectron volt, and up conversion. So T1 to S1. So the gap is 13.4 millielectron volt. It's quite small delta ST we could get. Because of this small delta ST, we could accelerate reverse intersystem cost impact. Okay, so this is the OLED behavior. OLED show the maximum EQE close to the 20%, and wavelength was 471. It's pretty good behavior we could get. So last 1 year, so the development of the TADF is very competitive. I'm very happy to see another researcher's results, and it's very exciting. So okay, I'd like to show you another 3 examples. So our material show the risk rate of 1.9 times 10 to the 6. It's pretty good, and transient lifetime is 715 nanoseconds. And Professor Yasuda, he's also in the Kyushu University. He designed these 2 new molecules containing sulfur. So he found the introduction of the sulfur is also effective to accelerate reverse intersystem crossing rate, and he could get the risk rate of 3.5 times 10 to the 6. And Professor Kaji in Kyoto University, he designed a kind of the intermolecular CT complex. It's a bridged structure. He showed almost 10 to the 7th, very first risk rate he could obtain. And very recently, Professor Dr. Aizawa, he is now in Riken. He reported the very advanced TADF molecules. Actually, he combined both tetramethyl and sulfur unit. So here you can see MCZ TXT contain both 4 methyl groups and sulfur. And surprisingly, so risk rate reached to the almost 10 to the 8th. Very first risk rate he could obtain. So molecule is quite interesting. By designing, tuning just the methyl group and just introducing the sulfur, we can accelerate risk rate. But fortunately, I'd like to say, so if we increase the risk rate, actually, so oscillator strength from a single stage, I mean a KR decreased. It's vice versa. So it's okay. So if only focus on to increase the risk rate, we lose the KR. So actually, our molecule is very much well balanced. So the KR still we can keep the 1.7 times 10 to the 7th. So KR is the fastest. But if you look at, for example, the Kaji Sensei's materials, so KR is 10 to the 6. So the oscillator strength from singlet becomes slower. So this is one of the problem. So we should carefully design the TADF molecules by tuning risk rate and KR. Okay, and in their OLED device, not only a risk rate, but we also have to think about the FLET efficiency. So that is the next story. So this is the hyperfluorescence. Dr. Itindi and Dr. Chan and Dr. Tanaka, our team works very hard to customize, optimize the hyperfluorescence system. So MCVP is the host, and HDT1, this is the TADF assist dopant that generate exciton and transfer energy to the fluorescence emitters. So basically, we forced to generate exciton as the TADF materials. So we have a 25% singlet and a 75% two-bit, and we convert two-bit into singlet, and we forced to transfer all singlet to the terminal fluorescence over TADF function materials such as CZB and CZ, and it works very well. So the key is the we have to realize very efficient FLED, and simultaneously we should suppress the texture process to keep the high efficiency. So HDT1, this is Dr. Chan designed this molecule, and we always try to make a blue shift. Okay, this is the one previous materials. This material show the PL peak of the 495. So we try to blue shift, and by changing this carbazole into terphenyl unit, we can almost 10 nanometer blue shifted, 486 nanometer, and this grade is very good, 9.2 times 10 to the 5th, almost 10 to the 6th. And actually, we combine Professor Hatakeyama's Davna materials. We generate exciton here and transfer Hatakeyama sensei's MR material and gets the emission from Davna. So HDT1 has the emission spectrum here, and Davna has the absorption. So through this overlap integral, we can transfer the energy from TADF into the Davna emitter. Okay, actually, we prepared two sets of the device. One is the single layer device, the other is the tandem structures. So in case of the single cell, it showed the EQE over 20%, and of course the tandem showed the EQE higher than 40%. And okay, the lifetime is the LT95 was almost 10 hours continuous operation. And with the tandem structure, we can improve for 1.5 times. But okay, we also further try to improve the device lifetime by employing the mixed host system. So the mixed host systems, so Steve explained the extension of recombination site is very effective to enhance the lifetime. So I'm sorry, today I can't disclose the chemical structure of the host S1, but anyhow, it's the same thing happened. And then it showed the LT95, almost 65 hours continuous operation. It's very, very effective to expanding the recombination site. But in these devices, we have two problems. One is the FLED efficiency is limited to 67%. So if we decompose the emission spectrum with the HDT1 and the Davna, we have 33% of HDT1's emission. So I mean, FLED is not perfect. Also, we have a direct exciton formation by Davna because of the hole trapping, and this is the proof of hole trapping by Davna. So we apply the pulse voltage to the device and turn off the device. And the TADF only device should very clear decay without showing a spike. But in case of the hyperfluorescence system, you can see appearance of the spike. This corresponds to the trapping of hole charge carriers by Davna. So we have to overcome two issues. So actually, we changed terminal emitters. So here you can see the three materials: CZBN, CZBN, and Davna2. And this, particularly for the CZBN, these materials show the very nice behavior. So again, through this overlap spectrum, we can transfer the TADF exciton to the terminal emitters, and the PL is pretty good, almost 95, 99, and 90. Very high efficiency we could get. Also, the spectral width is also quite narrow, 26, 32, and 28. And so here you can see in these materials, we could completely transfer the energy to the terminal emitters. So it seems very much promising. Okay, here you can see OLED behavior, and all devices actually show the EQE quite good, over the 20% EQE, and EL wavelength is 471, 480, 471, and the lifetime LT90 is the 39, 28, and 16. So Davina showed a little bit quick degradation, but CZBN, these materials show the very much good lifetime behavior. So I'd like to explain the two issues. So one is the very efficient FLED from TADF into terminal emitters. So I mentioned that the FLED happened through the disoverlap integral. So black line is the HDT1 TADF emission spectrum, and these solid 3 lines show the absorption of the terminal emissions. So through this overlap integral, FLED happened very efficiently, actually 100%. And this is the transient decay. So black line is the only TADF emitters. So you can see prompt and a delayed emission. So once we introduce the small amount of the TADF, a small amount of the terminal emitters, you can see the shortened the delayed lifetime. In case of the CZBN, very efficiently shorten the lifetime. So that means FLED is very efficient. So because of the FLED efficiency is higher than the ISC, so we can make a shorter delayed lifetime. This is a proof of the efficient FLED. Okay, another issue is the carrier trapping effect. So here you can see an energy diagram of TADF, AD, and the 3 terminal emitters. In case of the CZB and CZ, so the HOMO, LUMO is well aligned. In case of the Davina too, so because of there's a shallower HOMO of 5.38, so whole carriers tend to accumulate here. So but CZB and CZ, because of the alignment, so whole accumulation, we can expect less accumulation in this case. So as expected, so the pulse operation show that in case of the CZB and CZ, so the pulse spike appearance is very much limited. On the other hand, CZBN, you can see a small appearance, and in case of the Davina, we have a very large appearance of spike, indicating the accumulation of charge carriers. Okay, so I should update the lifetime of TADF materials. So our startup, QLux, works very hard, and previous SID meeting, they disclosed our cutting-edge technologies. So the late emitter bottom emission, LT95,000 candela, almost 40,000 hours. So green is also over the 20,000 hours. But still blue is still limited, but it's getting better and better. So bottom emission, the LT95 is 280 hours, continuous operations. Okay, I'd like to summarize my talk. So today, I updated our TADF activities. I mentioned the possible TADF up conversion mechanism, and also I mentioned the device lifetime. The best one is one of the best ones show the LT95 over the 67 hours with the emission wavelengths of 472. So hyperfluorescence system seems very interesting, containing many photophysics. We very much enjoy photophysical behaviors. Okay, finally, I'd like to thanks to our research members. Also, I'd like to special thanks to the Professor Hatakeyama for the collaboration with his exciting development materials. Also, I'd like to thanks to the funding agency, JST Electro, Next Evo project and QX. Okay, thank you very much for attention.
Okay, thank you very much for your excellent presentation. And this presentation is open for questions or comments from the speakers.
Chihaya, hi, this is Steve.
Yes.
Really wonderful talk. I have a question for you, which is, you know, Thomson's been working on these TADF molecules with metal linkers. Mm-hmm. They also have very fast lifetimes, particularly the silvers, which are in the, well, low hundreds of nanoseconds lifetime. What is your opinion on those versus the purely hydrocarbon type of TADF molecules? What do you think about the metal linked materials in that context?
So you mean the Q plus copper complex?
Well, he's done copper, gold, and silver, published on all of them, and the silver is particularly fast. The coppers are on the order of a microsecond, as you saw. Mm-hmm. But the silvers are like 300 nanoseconds and so on, and the golds are somewhere in between.
Yes, I think actually the metal complex is also interesting, and the silver, copper, also even in a zinc, can make a shorter up conversion speed. So the even kind of like metals works very efficient. So and I think the key is if we can change the electronic state of singlet and triplet, we can quickly upconvert. We can accelerate the SOC, spin-orbit coupling. So by engineering the S1 and T1 wave function, and the metal complex, it has the flexibility for designing of the such wave functions. So I think still, pure aromatics, also the metal complex both is very, very interesting subject.
Thank you. It's nice to see how much progress you've made. It's really quite amazing.
Okay, is there any question from speakers? Okay, then if not, then let's thank the Professor Adachi for his excellent presentation. And also there was a question about the previous presentation. Actually, one audience asked about the cost of deuterated iridium complexes compared to the conventional iridium complexes. And then the answer from the speaker is that maybe the cost can be 2 times, at least I think 2 times higher than the conventional iridium complexes if you use deuterated ligand in the phosphorescent emitters. Okay, then we will move on to the last presentation of session 1, and the speaker is Dr. Jun-Yun Kim. He is the leader of TADF and phosphorescent development team of LG Display. His title is Development of Next Generation Wide Color Gamut Displays Through Relationship Between Narrowband Emission and Luminance in OLED Applications. Let's welcome Dr. Jun-Yun Kim.
Okay, thank you for your introduction. Yeah, it is great honor to have this opportunity for presentation. Also, thank you for inviting me again. Okay, let me introduce myself. I'm Jun-Yun Kim, working for LG Display in the field of next generation OLED material and device. Today, I'd like to talk about development of next generation wide color gamut display through the relationship between narrowband and emission and luminescence in application. Okay, the presentation is divided into 3 parts. First of all, I'm going to talk about OLEDs in our daily life at introduction. Following our topics are OLED special feature and then breakthrough technology. First is introduction. This page was already explained at last year's KAST Symposium, but I will explain it again because it is very important for the change of display in our daily life to come. Displays has been around us just as changing their shape. After first and the second industrial revolution, we can approach a lot of information with CRT TV, which is a first entry-level TV product. But because of its relatively high cost at that time, we used one display with many people. As developing second generation TV, that is PDP and LCD, and finally, one person can use many displays. It made get information easier as selective and one-way display. Now my question is about third generation. An answer may be a bidirectional communication with displays melted to our daily life. It became possible due to post-industrial revolution, which means no limitation on time and space. Therefore, in the future display, structural advantages such as a form factor is very important. Unlike the LCD require a backlight with complicated structure, OLED with self-emission characteristic have a simple structure, making them thin and light display. In addition, the future will require flexible feature unlike flat panel displays such as conventional LCDs. In this point, OLED is a display having a wide viewing angle without light leakage and curved condition because it shines itself without using liquid crystal and the process advantage of deposition on plastic. So LDG prepares a whole range of OLED portfolio from the wearable, automotive, mobile, IT TV to the commercial display. So future strategy is the expansion of small and middle-sized PHOLED to prepare for the future in various fields, and the megatrend of large-size OLED to different product development through OLED innovative technology. Therefore, in our daily life, future OLED will always be with us in automotive and aircraft, and smart home and city. Okay, next content is OLED special features. Let's just remember this OLED is ACE. To help understanding, I will briefly explain the comparison with the current LCD technology. First is initial A. Unlike LCD local dimmings, OLED is pixel dimming is possible. So perfect flag is enabled to enhancement of perceived luminance. With this feature, a curated color expression is also possible regardless of gray level. In addition, since no liquid crystal is used, it has the wide viewing angle characteristic without change of color and brightness. Second is initial C. Recently, we spend our time with many displays such as school and company and public place. OLED has low blue light and flick-free features compared to LCD, which reduce eye stress, making it a more comfortable display. Also, it was first certified by several accredited organizations such as TÜV Rheinland and iSafe. Okay, finally C. Also, it is an eco-friendly display with less hazardous substance when it is made and excellent recycling efficiency after it is made. Okay, the advantages of OLED that everyone knows are up to here. Let's talk about breakthrough technology to upgrade into better OLED. Until today, OLED was challenges for a reason that LCD can't replace. Breakthrough of OLED are from wide color gamut and image quality via high resolution and design flexibility called rollable and foldable and stretchable, and to differentiating factor with LCD, transparent, crystal sound OLED revolution in value addition, and automotive and furniture architecture toward new application. There are many applications that use the advantages of various OLED like this phase. Let's focus on the image quality directly related to the light emitting characteristic of OLED. Okay, OLED Emission itself. This sentence is an essential sentence in LG displays OLED, and there is a way for us to improve into the sentence. To give the answer first, the material that is self-emissive to itself is the easiest and the most accurate solution. Okay, this page shows the currently commercialized OLED structure for each size. A large area OLED uses a stacked bottom emission technology to have a good viewing angle when it has a similar PL and electroluminescence spectral shape. On the other hand, small and medium-sized OLED, which are products with strong individuality, use a strong cavity and the top emission structure with specialized efficiency and color into the front direction. For about 10 years, these two technologies have developed, and the structural technology of each device is almost saturated, and there is a limit to the luminescence unless the material in each structure does not change. Okay, first let's talk about small and medium and sized plastic OLED. Fortunately, real black and freeform design and transparent of OLED features replace various displays in automobile. However, unlike TV and mobile, it has to endure harsh conditions such as high temperature at desert and low temperature in winter, and humidity and UV ray. Therefore, the device requirements are brighter and more stable and longer lifetime than of mobile. So the single device for mobile that requires low power consumption and the two-stack device structure for automobile require higher efficiency and longer lifetime. Both applications, which are already mass produced in an optimized structure, require materials innovation with narrow luminescence and long life technology. If the EQE at plastic OLED is almost saturated, the improvement of the sharpness of each color RGB is proportional to the white efficiency. For example, the current used top emission method improves the efficiency and the color purity of materials with a fluoride half maximum of around 60 nanometer through the strong cavity technology. If the color purity of the materials is improved, the cavity loss will be reduced compared to broader emission materials, and the white efficiency will be improved, and the lifetime at same luminescence will be increased. In conclusion, the color purity of material is enhanced to the improvement of luminance of lifetime. Okay, recently, many papers on fluorescent and post-fluorescence and TADF material having a narrow fluoride half maximum and high efficiency have been published. The detailed their principle and the effect of each material will be explained by following presenters. LG Display evaluated some of these materials, and it was found that the narrower FWHM in same chemical core group, the longer lifetime. Therefore, improve the chemical stability of materials with such narrow characteristic is the biggest hurdle for product application based on reliability. Okay, based on the device results, let's find out the relationship between color, brightness, and lifetime. The human eye has a relative sensitivity to color. Any color of RGB has the same effect in top emission, but narrow emission is in first peak of LED is selected for better understanding to explain example of top emission effect. Because second peak intensity of blue and green is related to increase of candela in considering of relative sensitivity to color. So we fabricated two OLEDs. One is bottom emission and the other is top emission by using a different emitter. In comparison of broad LED and BR and narrow LED NR is the same bottom emission and the top emission current efficiency. Regardless, BR's EQE is 20% is higher than that of NR's 50% of EQE. This is because the cavity loss and the NIR region elimination of NR is minimized due to the effect of the 18 nanometer narrower FWHM than that of the BR. The slight increase in the relative lifetime at the same luminescence is thought to be due to the device effect in the change of the between and bottom emission and top emission. Additionally, it was found that these lifetime characteristics were more dependent on chemical stability of their core group. In terms of product viewpoint, reliability has the highest priority over other characteristics because without reliability, there is no product. Okay, next is large size OLED. And the large size OLED depend more on the intrinsic property of the material. In terms of material, we can improve color and brightness with applying deeper and narrow RGB materials in emissive layer. For this three-stack structure, increasing efficiency of blue directly lead to improvement of total brightness because bottleneck of white brightness is blue. In addition, color gamut is also improved through a different color adjustment in second step. Therefore, with high color purity material, it enables us to make more various device structure in future. Okay, let's learn more about color double OLED. Currently, double OLED is a method in which one device pixel emits white color, and the change in the white spectrum determines their efficiency and color gamut. For example, as shown in the data presented at an SID conference, improvement of DCI coverage and the peak and full white luminescence were achieved together through a three-color structure with narrow LED just added in the three-stack and two-color structure. Okay, therefore, future technology having a narrow spectrum is directly related to white efficiency, and especially narrow blue and red undoubtedly improve color and efficiency. So what about green? Here are two spectra with the same efficiency. Which one is better? If we consider white, it is good to include white color, but if you consider color gamut, you will have to choose one peak material. Therefore, in the white technology, which take many spectral considerations, the improvement of color gamut does not necessarily lead to increase in the white efficiency. Okay, let's talk more from a product viewpoint. If YG color is excluded, color gamut and white efficiency are proportional to both pure LED and double OLED. In this case, if the lifetime improved, what about the luminescence and the color? Here are two materials, A, B, with the same current efficiency. if B material with the overall spec of product standard at the same 1000 nits. Assume that it has the same lifetime at 1200 nits. In this case, the increase of current is accompanied by the increase of power consumption, because power consumption is consists of voltage and current. However, if the voltage can be reduced without decreasing the lifetime by using another layer, it can be used if the power consumption is equal. Also, in this case, the two-stack and the three-stack structure, which allow more tunable than the single structure, will be advantageous. Therefore, in the case of material, with an increased lifetime, it may be considered to be used a brighter OLED by adjusting the device path. Considering all these factors, LG Display is developing next generation device with narrow emission and high efficiency technology. In particular, it is underdeveloped, focusing on Fluorescence and Hyperfluorescence and PSF device. And the priority of development is blue color, is always blue color, and followed by green and red. The necessity of blue cannot be overemphasized. To do so, OLED engineering must first determine their application, as determining the operational mode as a targeted application. Communication and feedback must be made after material and device evaluation. And the molecular design must also be developed with targeted properties for targeted OLED performance. The OLED developed in this way will be filtered and confirmed according to the application requirement. And only one material, each layers, and the device of one condition are used in the panel. Therefore, the product has very strict control specifications, so the targeted strategies for the product is required for the adoption of new material. Okay, finally, for better collaboration, companies and university and institutions should communicate more around OLED development, because the highest priority for better OLED is needed to the innovation of materials, our future partner, with our future partner. Okay, thank you for your attention.
Okay, thanks for the presentation, Dr. Jun-Yun Kim. So this presentation is open for questions or comments from speakers. Okay, I have one question about your presentation. So you mentioned some like a phosphor and TADF systems in your RGB colors. Can you comment on the current status roughly? Which system is yeah.
Implementation is top secret in our company, but I prepared my presentation in appendix. Please show my presentation.
Yeah, please show the presentation file.
Yeah. Oh. Okay, move the. Okay, this page is our current status of RGB by using a narrow RGB technology. In this figure, shows the mass production material compared with our narrow RGB OLED device. This is including the phosphorescence and hyperfluorescence and PSF. red is almost the same status of yeah, previous material, and green is also we achieved 60 and 70 nanometer in case of white color, but in blue is almost 30 and 40% compared with their fluorescence blue. So well, this is our current status in next using next OLED. Yeah.
Okay, thank you very much for your answer. Okay, then let's thank Dr. Kim again for his wonderful presentation about OLED. Thank you again. Okay, this is the end of session 1, but before closing this session, actually, Professor Adachi, actually there's some questions from the audiences. Professor Adachi, can you hear me?
Yes.
Oh, yeah. So one audience asked about the triplet extons in the hyperfluorescence system. If you use a triplet, if you use a TADF material as the final emitter, then in that case, of course, triplet extons will be used. So he is wondering the effect of triplet extons on the device performances.
Yes, I think that is the most critical issues, and actually, we already overcome this issue, and probably next chance we wanna talk about the detail. But yeah, that is a very critical point.
Okay.
And we have a solution. Yeah.
Okay. Thank you very much. Okay, then this is the end of session 1, and we will have a 10-minute break, and then we will start the session 2 after 10 minutes. Okay, I hope you enjoy the session break, and we will start session 2. But before starting the session 2, actually, there's some question from audiences, and one question was about the narrow-emitting emitter. One audience asked about the effect of narrow emission on the angular color distribution of the OLED. Dr. Jun-Yun Kim, can you answer? Yeah.
Okay, that is dependent on OLED application, such as PO and TV. And basically, issue of viewing angle occurred by different of PL and EL spectra. In case of PO, using a tab emission method, is now status is bright half maximum is about 30 nanometer. So, you know, in narrow spectrum, FWHM is smaller than in this value, but there is no problem. And the case of TB is weak cavity of bottom emission. That is same, and PL and EL spectra is there is no problem.
Okay, thank you for the answer. Okay, then we will start session 2, and the first speaker of session 2 is Professor Takuchi Hatakeyama from Kwansei Gakuin University. I think he is very famous, and he is the pioneer of boron-based TADF materials. His title is Recent Progress in Multi-Resonance Effect-Based TADF Materials. Let's welcome Professor Hatakeyama.
Thank you very much for your kind introduction, Professor J.Y. Lee. And I also appreciate this invitation. It is my great pleasure and honor to speak to you in such important symposium. And let me share the materials. Can you see the my slide? Okay. If okay, I will start my presentation. The voice is okay? No problem?
Okay.
So let me start with a brief background briefly. And as you know, the fluorescence dopant can utilize only singlet exciton, and phosphorescent one can utilize both the singlet and triplet exciton via a rapid reverse intersystem crossing, and which was established by Professor Forrest. But even with half the efficiency of fluorescence emitters, the commercial OLED display still are employing the blue fluorescence emitters shown here. There are two major reasons why we need to use fluorescence blue emitters. The first one is device lifetime, as mentioned in the earlier presentation lectures. And the second one is color purity. Besides LC type emitters, the phosphorescence dopant emit broader emission spectra than the fluorescence one. So we need to use a color filter or an optical microcavity to improve the color purities, which is accompanied by efficiency loss in the display application. So, and even the fluorescence emitter exhibit useless light. So we need to continue to develop narrowband emitters for the display applications. To achieve the narrowband emission, we always faced with intrinsic problem by Brownian spectrum. So here I show you the pyrene and the peridine. They have a very rigid molecular framework with small polarization. So in that case, we have only a small structural relaxation and stock shift in the excited state. But even with such a rigid molecular framework, we have a broad spectrum due to the vibrational structures, which was which is caused by vibronic coupling between the electronic transition and stretching vibrations. So we can predict, we can estimate vibronic coupling by just checking molecular orbitals. So if we have S0, S1 transitions, this bond loses electron, and this bond gains electrons. That means this bond gets longer, and this bond gets shorter. So this is obviously observed in the optimized structure of S0 and S1, colorized in the green and blue color. You can see the obvious stretching vibration in optimized structures. So as a result, we have we always achieved several emission peaks, as shown here, which are corresponding to each electronic transitions from the ground state of S1 to each vibrational state of S0. And this is simulation of vibronic spectrum of perylene. And you can see the simulated red spectrum roughly agrees with experimental blue line. So, and the green stick bands are corresponding to each vibronic transitions shown in tables. And this energy is relative frequency energy is up to the 3000 wave number, really large, and causing the broadening of spectra. And because vibronic transition include 6 stretching and bending mode, ranged from 300 wave number to 1600 wave number. So, and in particularly, this second peak is consisting of 3 stretching mode with large line density. So anyway, we need to suppress such a vibration, stretching vibration. To suppress it, we need to decide to use resonance effect of boron and nitrogen atoms. The resonance effect of boron is easily drawn by just drawing these 3 resonance structures, which have the positive charge at also polar position to the boron atom. This is also this is related with molecular orbitals. So you can see the LUMO is localized at also polar position to the boron atoms. And HOMO is not affected by boron substituent because HOMO is much lower in energy than the vacant orbital boron atoms. And in contrast, nitrogen has a lone pair, so we can draw the 3 resonance structure with negative charge at also polar positions. So this is again we can is enhanced HOMO, and HOMO is localized as also polar position to the nitrogen atoms, and the LUMO is not affected by nitrogen atoms. So this is our molecular design by multiple resonance effect of boron and nitrogen atoms. So if we put boron and nitrogen to the benzene ring as a 1-2 position, we can obtain alternating localization of HOMO and LUMO, as shown here. You can see the HOMO is localized at also polar position to the nitrogen atom, and LUMO localized at LUMO is localized at also polar position to the boron atom. And these frontier orbitals is localized just above the carbon center, not between the carbon center. That means this molecular orbital has a non-bonding character. So as a result, there is no obvious bond stretching between the optimized structure of S0 and S1, just a small twisting. And there is no obvious vibrational peak in the emission spectra. So we can have a very sharp emission band. And also importantly, PLQI is always around 90% because non-radiative process is mostly caused by the stretching vibrations. So we can have we can always have a narrowband emission and high PLQI by using the multiple resonance effect. So this is again the simulated spectra. So the red one is a simulated one, and the blue one is a experimental one. Now, there is a small difference, but it's okay. And you can see the green stick band corresponds to the barbaric transition. And the energy splitting of each barbaric transition is very small because they consist of the twisting or bending mode with smaller energies. So this is why we have a very sharp emission band. So this is also important part for synthesis of double derivatives. So actually, I'm a synthetic chemist, so I emphasize this part. We chose the starting material here, aryl chloride, and the first step is recession and transmutation. We can put boron substituent here, and this intermediate undergoes tandem fluid class reaction in the presence of Hunich base and under the elevated temperature to achieve the double CV bond formation. And we obtained a double one in 32% yield. And this methodology is we call it a one-pot operation and a faster and robust methodology, which can provide industrial production. And also importantly, such easy access to the structure can allow us the fine-tuning the structure, easy fine-tuning of structures. So people can easily get a higher or better performance of the compounds. This slide summarizes multiple functions of multiple resonance effect. The first one is acceleration of polar fluid plus reaction. As shown here, you can see the nitrogen lone pair push to the benzene ring and push the electron, and the benzene ring can react with boron center. This is also the resonance effect. And the second one is suppression of barionic coupling between S1, S0 transition and stretching vibration. We can have a sharp emission band. The third one is suppression of non-radiative transition via stretching vibration, which can provide high PLQI. The fourth one is to increase the CV bond energies, which can provide sufficient stability for practical use. I will show you the next slide for this part. So this slide shows bond dissociation energy of CV bond. And, I chose the two model molecules, triphenyl-boron and phenazoborine, to compare with the double one. So, and I focus on the radical cation species because boron has a boron is a positively charged atom, so CV bond is weakened in the radical cation state. And you can see the boron bond dissociation energy of these two molecules is much smaller than the double one because of resonance effect and the structural effect. And if we focus on the Gibbs free energies, the bond dissociation energy of these two molecules decreases a lot. But double one still have a large bond dissociation energy because CV bond cleavage process provide two molecules. That means the process gain the entropy. So the dabna is free from entropy gains. So this is also important factor of to stabilize the CB bond. And also this is why we could not use the conventional organoboron material in the emitting layer. And the fifth one, the final one, is related to the TADF properties. And actually, TADF OLED was established by Professor Adachi 10 years ago, and we have already have a nice lecture, so I will skip the details of TADF. But I want to say that that multiple resonance effect is also useful to reduce the ST gap to facilitate reverse intersystem crossing. This is a basic photophysics data of dabna 1. So as we expected, the homo-LUMO separation can provide small ST gap, as shown here. The energy splitting between fluorescence and phosphorescence is 0.17 eV. This is acceptable values for TADF. And fortunately, we found degraded fluorescence during a transient PL analysis, and the KRC is calculated to be 10 to the 4th. Actually, this is not good for the display for the application. So we designed a new dabna with fused dynamic structure of dabna 1. So because of the extended pi skeleton, ST gap is further reduced to be 0.02 eV, and again KRC reached to the 10 to the 5th. So this is a promising result. And to achieve maximize the properties, we usually use quantum chemical calculations. And actually, such a calculation is really powerful for the OLED development of OLED materials, but not for our materials, because conventional TDDFT calculation overestimate exchange interaction of multiple resonance effect-based materials. So you can see the ST gap is calculated ST gap is much larger than experimental ST gap. Actually, there is some trend, but these results is not useful for the fine-tuning of the molecular structures. But recently, Professor Olivier reported that the double electron excitation method, such as CC2 or ADC2, can roughly reproduce a ST gap of multiple resonance effect, multiple resonance-based TADF materials. And now we can somehow achieve the fine-tuning of the molecular structures. And I also say that the SOC of our material is very small, because the molecular structure is really flat. So, but there is considerable room for further improvement of SOC by molecular structure tuning. Also, this is again the synthetic part. Actually, maybe people will not synthesize new dabna because it looks very difficult to synthesize. But we developed a one-shot boleration. The previous one is one-pot boleration, but this is one-shot boleration, the advanced one. So if we have such a allyl amine precursors, it has a high HOMO energies, and the HOMO is localized as the central benzene ring. So just treatment with BBr3, we can achieve the selective double boleration reaction to get new dabna in the moderator yield. Actually, yield is much higher, but purification is difficult. And this precursor is easily synthesized from the commercial available sources. So now we can synthesize a lot of structure like a Doubner or new Doubner by using the one pot and one shot population reaction. So please check the review for the synthesis. And this is OLED performance. You can see the really sharp emission band, which is comparable to the inorganic emitters, such as gallium-based LED or cadmium-based quantum dot. And you can see the high EQE even at 1000 nit because of the high KIC and also the high horizontal dipole ratios. Unfortunately, so LT50 is not so long, actually a miserable data. So we need to combine with assistant dopant to achieve the longer device lifetime for the practical applications. And recently there are a lot of multiple resonance-based TADF emitters, and we can easily modify the performance by structural modification, such as ring closure or addition of the donor or acceptor groups. But such a modification always accompanied by red shift of emission spectrum. So keeping deep blue emission with higher KIC is really difficult for us. But this is one solution, the oxygen atom incorporation. So if we, you can see the HOMO and LUMO of new Doubner. The HOMO-LUMO spread holds the molecular structures. But if we put oxygen, we can obtain restricted HOMO conjugation. So in that case, deviation of energy deviation of HOMO is much slightly smaller than the deviation of LUMO. In that case, we have slightly larger than the deviation of LUMO. So in that case, we can have a larger HOMO-LUMO gap. So that as a result, we had slightly blue shifted emission spectra shown here. And fortunately, the EQ is also high, and LT50 is much longer. So this is a promising result. And this is not a published one, but we have tried several approaches to achieve the deeper emission, deeper blue emission, and higher KRC. And this is one successful result. And you can see the emission maxima is 458, and the peak is still very narrow. And the KRC is 10 to the 5th. This is, I think this is okay for the display applications. And another approach is, another result is here. The peak is too blue, but the KRC reached to the 10 to the 6th. This is a kind of a record of performance for multiple resonance TADF materials. And we are now focusing on these derivatives to achieve some applications. So this slide shows the other core structures. We are trying to make new core structures, just combine Dobner and Abner structures. We have a fully resonating extended pi skeleton by just combining these core structures. And actually, the device performance is not so good, but this is acceptable EQE for, and also the nice emission band for the green color. So this is we should push the blue emitters, but we also working on the green or red emitters. I appreciate my student work. They work very hard every day. So, and also I thank the collaborators as shown here and the financial support. Especially I appreciate Genshi Corporation and also the Professor Adachi and the Sumitomo Chemical Corporation to provide nice collaborations. That's all. Thank you for your kind attention.
Okay, thank you for your informative presentation. Actually, I have some questions from audiences. So one audience asked about the transient PL data of the boron compound. Actually, in your slide, some boron compound show like some mixed decay in the delayed fluorescence region. Can you comment on what the origin of that decay, like a double exponential decay or something like that?
Oh, so decay curve?
Yeah, decay curve. Yeah, some compound like show two-step decay or something like that.
I see.
Yeah.
Actually, I think usually we the single is okay for us.
Yeah.
And sometimes the background is very high, so it looks a double exponential, but this is because of the high background. So we have a background here, so we obtained such a curved transient decay curve, but this is almost a single exponential one.
Okay.
Make sense?
Okay, yeah. And also there's another question is like about the simulation. So in your calculation of SOC, so then he is asking about the method to calculate the SOC.
Yes, sorry. Here the method, we use the simple BCLP DZB by using a Zora method, which is implemented in the ADF, commercially available sources. Actually, the SOC is highly depending on the method, as you pointed out. So I'm not sure that this value is accurate or not, but at least as we have much smaller values than the donor acceptor type of molecules, so we need to improve it by changing the structures.
Okay, thank you. And I think Dr. Kim has a question about your presentation.
Yeah.
Oh, yeah.
Okay, thank you for your presentation. Can you hear me?
Yes.
Yeah. In the next device structure using HF and PSF, is BN material such as Davuna shows good property as an end emitter with small delta EST. So, however, the deposition of materials with molecular weight is bigger than in 10 gram per mole is difficult to our process. So, could BN structure remain a chemical backbone or some core group with a molecular of middle weight that of Davuna, besides that, Davuna and mu Davuna in the BN structure? In my question is there is some freedom of chemical group such as BN and mu Davuna of middle of weight.
So you mean the smaller molecules?
Yeah.
Yes. Yeah. Actually, it's always we face with always such a problem because actually the pi if we have a larger pi skeleton, we always obtain the smaller ST gap because nice separation of the HOMO and the LUMO. But we always obtain the larger molecular weight, so it's very difficult to reduce the molecular weight if we need a high KRSC. But there are several ways to keep molecular weight small. For example, we can add some 3D structures. This is a very planar, but if we have tilted structures, we can gain the SOC without extension of pi skeleton. And also the heavy atom effect is a candidate, but such a modification always accompanies by degradation. So we put distortion of a heavy atom. That means we put a weak point of the structure, and also we often observe the reduced degrees of PLQY. So that is a really difficult target to solve. So, but we are trying to for the practical application, and I will maybe future I will provide you some solution.
Okay, thank you.
Okay, thank you. Is there any more question from speakers? Okay, if not, then let's thank the Professor Hatakeyama again. Thank you.
Thank you very much.
Okay, we will move on to the second presentation of the session 2. The speaker is Professor Lian Duan from Tsinghua University. Actually, he is an expert in the field of TADF and TADF sensitized fluorescent devices. And his title is Efficient and Stable Deep Blue OLEDs based on TADF sensitized fluorescence. Let's welcome Professor Lian Duan.
Can you hear me?
Yeah.
Oh, okay. Thanks, Professor Lee. It is my honor to give a talk at this very nice conference, and so and I think this is a really nice talk. The symposium has a very nice topic. What is the limit of the lifetime and the characteristic of OLEDs? And it is it is challenging, but it's worthy of hardworking. And so, here is the first a brief background. We know that now OLEDs are now becoming the mainstream display technologies, but OLED is also facing the challenges of other new technologies such as QD LED or PLEDs. And one of the advantages of these materials is that these inorganic materials, they claim they can have a narrower emission spectrum, and the narrower emission spectrum is very important for color purity. And here we can see that and the new standard for the HD TVs, and they not only required higher resolution but lower power consumption and wide color gamut. And it would be challenging to meet these requirements of in terms of efficiency and color purity and also lifetime, and especially efficient and blue emitters remain the holy grail for OLED materials. And here is a brief history of the evolution of the OLED materials. This is the first generation of materials developed by Qing Tang and co-workers from Kodak. And these fluorescent emitters, and even though they have lower efficiency, and they have a very long lifetime. And nowadays, as mentioned by the years speakers, we have to use blue fluorescent materials because of their long lifetime. And this is the second generation of emitters is the phosphorescent emitters, and first reported by Forrest and Thompson, and also Professor Ma and Professor Chi. And these materials, they can have higher efficiency, but the lifetime for blue is still limited and cannot meet the requirement for display applications. So that the scientists all around the world are searching for new generation of materials. And this and Professor Adachi published this paper 10 years ago, and in fact, more than 10 years ago, I think I read the early view version of this paper, and in January or February, I cannot hardly remember, of 2011, and it was a very exciting paper. At that time, I thought it would bring a great revolution to the OLED materials. These TADF materials, and they are fluorescent, but they can still be 100% in efficiency. But there are some conflicting factors in designing TADF materials, and we need to fine-tune the molecule structure to balance the overlap of the HOMU and LUMO to achieve both a small delta EST and a fast and radiative rate. And after reading the paper, we started to working on this idea. That is, we don't use these TADF materials as a final emitter, but we use them as sensitizers for final emitters, such as conventional fluorescent materials. We filed this patent, and actually in late 2011, and it was issued in 2016. And we called it TADF sensitized fluorescence, and for short, I'd also think it may be called a kind of a Tsinghua fluorescence. And we published our first paper in 2014, almost the same time, and Professor Adachi's group published their paper on this sensitization and in Nature Communication. And this is in our first work, we tried to reduce the singlet and triplet energy splitting of the sensitizer, even though the pure QI of these materials as the sensitizer is reduced. But when these materials are not used as a final emitter, and the pure QI of the doped system can be still efficiently high. We can see that here. We use this conventional fluorescent emitter DDAF as a final emitter, and we can see that it has the emission spectrum has a narrower and full width at half maximum, because it's pure fluorescent material, and its emitting is from its localized excitons, and instead of CT excitons for these TADF emitters. And in this early trial, the efficiency is not very high, but it's still higher than 10%, and higher than the conventional upper limit for conventional fluorescent emitters. And this is a paper by Professor Adachi, and I think this paper is published, and this paper was appeared maybe 1 month earlier than our paper, and in this approach, Professor Adachi called it TADF assisted fluorescence, and nowadays also hyperfluorescence, which is a very popular name for this kind of sensitizing scheme. And how to improve the efficiency of these sensitized systems? And so we need to find out the energy loss pathways and block them. And here in this diagram, we can easily find that the texture energy transfer from the triplet of the TADF sensitizer to the conventional fluorescent emitters, and also a direct charge recombination on the fluorescent emitters, would generate non-emissive T1 of conventional fluorescent dopants, so that these paths should be blocked. And we tried a chemical way, because both texture transfer and also the charge trapping, and they are short distance interactions, so that we choose a very simple isotope based green fluorescent dopant. We just increase the size by attaching inert and bulky substituents to the outer side of these emitters. We use just methyl, attribute to, and by increasing the size, we can see that the distribution of the front orbitals are not changed, but the distance between the molecules are increased, so that both Dexter transfer and the charge trapping can be greatly reduced. And in this, by using these emitters, we can achieve efficiencies around over 23%, and also with much improved lifetime. We think that the improvement in lifetime is due to the reduction in the triplet concentration, and we also try to and we also tried this this system with the host and the sensitizer and the final dopant, and we studied the relationship between the wide gap host and also the TADF sensitizer and the final conventional dopant, fluorescent dopant. And we find that this combination yield the best efficiency and lifetime. That is we choose the host that favors longevity and recombination. That is, hosts and electrons would first recombine on this wide gap host, and then transfer its energy to the TADF sensitizer, and then to the conventional fluorescent dopant. And in this system, we can achieve the very long lifetime and also reduce the efficiency ROAF at high current densities. And so, I think this TADF sensitizer system would be good for the solution of blue. And why blue is less unstable, and this topic has already been mentioned by the previous speakers, and because we can see that for the commercially used fluorescent emitters nowadays, and they have an S1 around in the blue region, but the T1 is much lower. Like for the uncertain derivatives, and the T1 is only 1.7 electron volt, so that even if TTA and TPA happens, the hot section would not carry very much energy that is larger than the conventional bond strength. This is conventional bond, but for phosphorence, this is the situation is rather worsened. We need the T1 to be around 2.8 electron volt, but the S1 should be even higher. So, and if TTA or TPA took place, and the hot exons would be very high energy, but for TADF, and their S1 is almost the same as T1. So we think a TADF would be an ideal system for achieving stable blue emitters. And this work was done by my colleague, Professor Jeon, and she carried out quantum chemical calculations, and she wrote this paper, and that is when choosing the building blocks for constructing TADF molecules, we should avoid using moieties with weak bond. And weak bond, we should not only consider the bond dissociation energy in the neutral state, but also in the high energy state, that is the positively or negatively charged states, and also their S1 and T1, so that we can see that this carbon sulfur is might not be good, and this we can see this CP is even worse, but conventional and carbon and carbon nitrogen, they might be okay. So that we try to construct a stable blue TADF emitters based on the guideline and just given by Professor Juan, and we just modified our we just constructed these blue emitters modified from this 2 CZPN reported by Professor Adachi in his famous Nature paper, and we just removed one cyano, so that this benzonitrile is a weaker electron donor, so that the emission is blue shifted, and and we can see we constructed 4 CZPN and 5 CZPN. Actually, I think Professor Jun-Yun Kim also independently reported these 2 emitters, and these emitters they are simple, and actually nowadays undergraduate students in their organic synthesis classes, and we can ask them to synthesize these molecules, because these molecules are really easy to synthesize. So these emitters, we can see that their emission colors are ranging from 440 to 480 in solution. But these emitters because the strength of the electron acceptor, its delta EST is not so small still, and we can observe an efficient TADF process in these emitters, and this is making this materials and really an important system for studying the reversed intersystem crossing. And we also tried to explain why these molecules can have a very fast reverse intersystem crossing with a not so small delta EST. You can see here, because the existence of multiple donors, so they can have an adjacent energy in the triplet states like T1, T2, T3 with Vibronene couplings, and they are closely packed, so that and they can, even though the delta EST of these materials can be large, and the upconversion is still they can be still very efficient. And we also made devices in this paper published in 2016, and we achieved a relatively long lifetime, actually the longest at that time. And in our later works, we try to understand why these molecules, why the steric effect can stabilize these blue TADF emitters, and we also need to decouple these 2 factors. That is the probability of the of TPQ, and also the degeneration rate, that is KTPQ, and we need to decouple these 2 factors, so that we use this magnetic field effect. We use the spin magnetic field effect to study these emitters, and we can see that at the low field and high field, and they show some opposite trend, because we can use them to study the spin mixing, and also this Zeeman splitting, and we can also change the voltage. That is the electron density in these systems, and also change the charge carrier balance in the systems to study TTA and TPQ. So that we made these very simple devices. Here is the simple MCPP host, and doped with these emitters, 5 CZPN and 5T CZPN. And then we try to use an insulating layer to change the charge balance, and we can see that the 5T CZPN can withstand a higher density of Hall carriers, in fact much higher Hall density than 5 CZPN. We can see that by increasing the thickness of the insulating oligomer type Teflon, we can see that the current are greatly reduced, and but for this 5T CZPN doped devices, we can see that even when the thickness of the layer reached 8 nanometers, and there's no big difference. We can see that. And then we also compared the TTA and TPQ, and for this 5T CZPN, and for the charge balance 5T CZPN devices, we can see a slight upward trend in MEL. And for the devices with this non-balanced and that is with an excess of holes, we can still see that and the increase we can observe increased negative MEL, so that our experiment shows that TPQ is the dominant degradation mechanism over TTA. And then we just compared these two systems. We think that why this 5T-CZPN is better than 5-CZPN, and we think that the blocking effect of the Dexter type of TPQ by these inert group and outer groups in 5T-CZPN would be the main cause. We can see that for this this is 5-CZPN, it cannot stand a very high unbalanced hole in current, but for the 5T-CZPN, it's okay even for the a very high unbalanced hole injection. We can see that because of the third butose, the coefficient of the TPQ can be reduced. So we also calculated the probability of the quenching, and by just which we need to find the weakest bond. And in this system, the weakest bond is this bond, the opposite to the cyano, that is this carbon and nitrogen bond. These bonds are the weakest for both systems. And actually, a bond strength in this 5-CZPN is even a little bit larger than this 5T-CZPN. But because the country, so that here we can see that for the probability coefficient, this one is smaller, but for the quenching rate, this one is much smaller. So that 5T-CZPN is would be stable than 5-CZPN, and we also try to find new ways to stabilize a 5-CZPN, and because this third butose and the molecular weight, they are too large, and the long and this 5T-CZPN cannot stand long time and evaporation in vacuum. So that we try to just, we also choose a deuteration, just as mentioned by which is studied by and mentioned by many previous speakers, such as the speaker from Samsung SDI. So, and this is very simple. Just we can get this deuterated 5-CZPN very easily by using a deuterated Carbazo. And we can see that this 5T-CZPN, we can see that there we can just from this IR measurement, and also this measured the energy. You can see that the energy is reduced. This is mainly from the carbon and the hydrogen vibration mode. This because deuterium is heavier than conventional hydrogen, so that it also helps to create a shallower potential energy surface. That is, that would make the coupling of the vibronic states more difficult, and thereby reducing the bond dissociation and make these molecules more stable. Here are the results. We can see that for the deuterated 5-CZPN, its emission spectrum is a little bit narrower, and efficiency is higher, and more importantly, and the lifetime is 3 times longer than this pristine 5-CZPN. These emitters are very stable, but because of the because of their broad and Forrest attack maximum, they are only they are not pure blue. They are only a greenish blue, and thanks to the contribution of Professor Hatakeyama, and we can use these materials as sensitizers for this multiple resonance emitters. And yeah, we can see here we try to use these 2 emitters. This molecule this is the famous new dabna reported by Professor Hatakeyama, and this is another emitter which is a little bit bluer than UW, and actually it was originally reported by a group of scientists in China, but later Professor Hatakayama pointed out that the actual molecular structure should be like this, and we use these two molecules as the final emitters. We can see that for this TSFA, we use this one as the final emitter, and it's blue, and this one and this new tabna, its color is a little bit red shifted, but these devices can have very long T80 for example for this one with the new tabna. We can see that its T80 is around it's over 450 hours, and we are and still this emitters cannot meet the requirement of the BT 2020 requirement, so that we should use we should find the final emitters that is blue shifted, and also we should find the sensitizers that are blue shifted, and then we try to work out on this system. Actually, in blue shifting the color of the sensitizers of these cyano-based emitters, we can see that with the blue shifting of the emission maximum, and their up conversion rate is also reduced. And how to solve this problem? And we just introduced multiple donor and other besides the introduction of multiple donors, we also introduced the multiple acceptors, and we think that this pi d pi and d pi d and a pi a structure would be ideal for constructing blue sensitizers. This is our work. This is some of in this system. We can see that here with even with P4. This is a deep blue emitter, but its up conversion is very fast. And we made devices using P4 as the emitter, and we also make this P4 as the sensitizer and the T-dabna, which is also a famous molecule first reported and modified from dabna and first reported by Professor Jun-Yun. And we just with this combination we can achieve peak efficiency over 30 and a relatively long lifetime for its CIEY. And this is still not enough, and we just extended this idea with this delocalized D pi D and A pi A structure. We can construct a new series of molecules and modified it not from not from a 5 CZPN but from a 4 CZPN, and its emission color is and like this, and their up conversion rate is at all very high, and more importantly, these emitters are very stable. This is the conventional 40 CZPN. Its peak efficiency is just merely higher than 20, but for this modified 40 pH, we can see that its efficiency is over 30, and its lifetime is 10 times longer than 40 CZPN. And we used it as a sensitizer for a deep blue and MR emitter. We can achieve blue shifted emission and also a relatively good lifetime in this system. And so I'd like to summarize as stable substituents should be chosen in constructing stable blue TF emitters, and multiple delocalized states are helpful for the improving of the up conversion. And I think the most promising solution towards deep blue is the use of TADF sensitizer with the MR emitters, and of course searching for new narrowband emitters with faster decay rates, and also new sensitizers with faster decay rates and also high stability would be very important for the realization of stable and efficient deep blue. And I'd like to thank my group members, and especially Dongdong Zhang, and this Professor Dongdong Zhang is now an assistant professor. And when he was he entered our group as a PhD student in 2013, and he's the first author of our first paper on this TADF sensitization, and he contributed a lot to our project. And this and as to the stable emitters, and Tianyu has done lots of work. And so I'd like to thank you for your attention again. Thanks.
Okay, thank you, Professor Duan, for a wonderful presentation. Okay, is there any question from invited speakers? Okay, I have one question. Actually, in your TSF system, actually, of course, the important thing is the host material. Also, for especially long lifetime. So then, can you comment on the strategy to develop the stable host materials for blue TSF system?
I think for this system, the first we need, of course, first we need to choose this stable substituents, and I think triazine and also benzonitrile, and also these are stable acceptors and stable donors, and they are very limited, just like a variation of carbazole and or indocarbazole, very limited. But in constructing the host, we need to construct a kind of cascade energy transfer, so that the host of the energy of the host is only a tiny little bit higher than the sensitizer, and the energy of the sensitizer is equal to or a little bit higher than the final MR emitter. And I'm also I also think that the axiplex host system reported by your group would be a very promising way. I'm now testing your axiplex system for our emitters, and I will share this results with you later.
Okay, thank you very much. Okay, thank you, Professor Duan, for your presentation. Thank you.
Thank you.
And before going to the last presentation of this session, Professor Hatakeyama, one question from audience.
Yes.
Yeah. So one audience asked about the effect of oxygen in your Davna-type molecular design. So how much the emission wavelengths can be shifted, and what is the reason for the blue shift if you use oxygen instead of nitrogen in the molecular structure?
In the molecular structure.
Yeah.
So actually, the one oxygen make a 5 nanometer blue shift about 5 nanometers, and that is all around 0.02 eV or something like that. And this is because of the restrict the conjugation. So because nitrogen has a high energy, lone pair of the nitrogen is higher than the benzene ring usually, but oxygen lone pair is lower than the that HOMO of the benzene ring. So conjugation is relatively weak. So that in that case, we have only a small energy splitting of conjugated new HOMO and HOMO -1. So in this case, the HOMO of the core structure is not so changed.
Okay.
But if we have a nitrogen, it can be increased. In that case, if we use oxygen instead of nitrogen, and if in that case the HOMO is maintained at lower than the nitrogen case, so in that case we have a larger energy band gap.
Okay.
So, is this okay?
Yeah. Okay, thank you. And Professor Duan, also there's some question. Actually, is it one audience asked about the overlap of the TADF sensitizer and the absorption of the terminal TADF emitter. Is it mandatory?
Yeah. I think it's mandatory because we need to have a very fast. We need to have a fast faster energy transfer rate, so that it would reduce the triplet density in this system.
Okay. Okay.
Okay.
Yeah, and also another question is in your deuterated 5 CGBN, it seems that the PLQI was increased by deuteration.
Right.
Yeah. So can you explain why?
Because deuterium is heavier, so that some vibration-related and non-radiative decay rates are blocked.
Okay. And Professor Hatakeyama again, there are many questions from audiences.
Oh, yes.
So one audience also asked about the reason why the FWHM is large if you use oxygen instead of nitrogen.
Oh, I see. It's not. It's a difficult question, but I think if we have oxygen, we can restrict the HOMO, but not the LUMO. So in that case, HOMO-LUMO transition has a CT character slightly. So I think which can causes more stronger interaction to the host materials. And then I think maybe the slightly broadened emission spectra. Actually, in the toluene, it's not so broad, but in the matrix, such as pi orbitals, we have a slightly broadened spectra. So I think that is why we have a broader spectra. But it's highly depending on the molecular structure. If we have a surrounding substituent, we can avoid such an effect. So it's highly depending on the device structure and also molecular structure. So we can regulate it.
Okay, thank you very much. Okay, then we will move on to the last presentation of this symposium. I am the speaker, and the title of my presentation is Ultrapure and Highly Efficient Blue Organic Light-Emitting Diode. So several speakers already mentioned the pure blue emitters, and also I will present our results about the pure blue emitters. And this is the content of my presentation, and I will mostly talk about the MR-type TADF emitters with only carbon and nitrogen in the molecular structure. Okay, I will skip this explanation because already several speakers explained the TADF materials, and we already know that it's possible to reach over 30% external quantum efficiency if you use TADF materials. So that TADF is very promising as high efficiency emitters for next generation OLED. And we have two options when we develop TADF emitters. One is a donor acceptor type TADF, and the other one is multi-resonance type TADF. If we use a donor acceptor type TADF, then usually we have a donor and acceptor, and free rotation is possible between donor and acceptor. And because of that, we will have a very strong charge transfer character, and then the HOMO-LUMO will be separated, and we will have a very broad light emission, and also stock shift is relatively large. Because of this, it is not that easy to realize deep blue devices using conventional donor acceptor type TADF materials. But if we use multi-resonance type rigid TADF materials, then the emission is very narrow, and also the stock shift is very small. So that kind of polycyclic aromatic hydrocarbon structure can induce short range charge transfer and also alternating HOMO-LUMO distribution. Therefore, this kind of multi-resonance type TADF materials actually are promising as the deep blue emitters. Already several papers reported deep blue boron-based emitters. Normally boron is included in the molecular structure with nitrogen, as Professor Hatakeyama explained. And we can see many papers about deep blue OLED with a color coordinate, Y color coordinate close to 0.1, and also the efficiency is quite high, sometimes over 30%. So these materials actually can show really good device performances compared to other TADF emitters. But it's very difficult to realize very deep blue emission with Y color coordinate of 0.05 corresponding to the BT 2020 standard, and also at the same time we need a very high efficiency above 20%, but it is not that easy to realize this kind of device performances if we use this kind of boron nitrogen based MRTADF emitters. So our approach to develop MRTADF emitters is to use just pure carbon and nitrogen. Actually, the carbazole is very popular as the electron donor in the molecular design of the TADF materials. It is an electron-rich moiety, but if we fuse the phenyl with the carbazole unit, then we can make an indolo carbazole structure, fused indolo carbazole structure, and that fused indolo carbazole has a relatively electron poor, so it can play a role of an acceptor rather than a donor in the carbazole. So in this table, you can see that we have there are several indolo carbazole based moieties, and if you check the HOMO and LUMO levels of these indolo carbazoles, then the fused indolo carbazole at the bottom has a very deep HOMO level and deep LUMO level, suggesting that this moiety is suitable as the acceptor moiety of the TADF emitters. And also one feature we can notice in the molecular orbital distribution is the alternating HOMO and LUMO distribution, like the MR structure. At first, we used this fused indolo carbazole unit as the acceptor of the TADF emitters. So we combined this acceptor with several donors. So we used carbazole and acridine and 2-acridine to develop TADF emitters. And in the molecular simulation, we can notice that the HOMO and LUMO are completely separated. So these molecules are donor acceptor type TADF emitters. And when we use the acridine as the donor, as you can see in the transient pair, we can detect delayed fluorescence from those two materials with acridine as the donor. And this is the device performances of the TADF emitters derived from the fused indolo carbazole acceptor. And the TADF emitters with acridine as the donor actually showed close to 20% external quantum efficiency, and the FWHM of this emitter was around 56 nanometer. As a conventional TADF donor acceptor type TADF, actually the FWHM is relatively small, and that's maybe due to the rigidity of the fused indolo carbazole acceptor we used in this molecular design. But we could not achieve like a MR type structure using the single fused indolo carbazole structure. Therefore, we combined two indolo carbazole moieties, two fused indolo carbazole moieties, and we developed TDIDCZ molecule here in this figure. Here you can see that the HOMO and LUMO of this molecule is separated in an atomic scale, so we can realize MR structure. So we can simply prepare this molecule by fusing in the Rockabazer unit. So we simply synthesized this TDI-DCG by two-step reaction procedures. In the emission spectra, the FWHM of this molecule was only 20 nanometer, very narrow emission. Delta ESD was 0.44 electron volt. The delta ESD of this molecule was relatively large because no electron donating and electron accepting element is included in the molecular structure. Therefore, this molecule showed only fluorescence without any TADF emission because of that large delta ESD. We fabricate the devices using this molecule, and the EQE was only 3.3% because it's a fluorescent emitter without any TADF emission. The peak wavelength was 401 nanometer, FWHM was 14 nanometer. Actually, it was a violet emitter rather than blue emitter because of the short wavelengths. We also synthesized some violet emitters by expanding the aromatic structure of the original TDI-DCG molecule. So we added the fluorine structure here, and then the extended aromatic structure may improve the emission properties of these MR-type emitters. You can see in the emission spectrum that the peak wavelength is 404 nanometer, FWHM 22 nanometer, and Shutok shift was 6 nanometer. And the PLQI was 71%, and the original TDI-DCG molecule showed PLQI around 50%, and the PLQI was dramatically improved by expanding the aromatic structure. And this molecule showed fluorescence emission, also violet emission, and the peak was 409 nanometer, FWHM was 22 nanometer, and also the spectrum was in the violet region, not the blue region, and the EQE was improved. Original molecule showed 3.3% EQE, but this molecule showed 5.1% EQE. So the aromatic extension could enhance the EQE of the MR-type emitters. But this emitter did not show any TADF properties, and we could not improve the EQE of this device further. In our original molecular design, the nitrogen unit of TDI-DCG was oriented in metaposition. That's why the emission wavelength is in violet region, not in the blue region. To shift the emission wavelength to blue region, we changed the position of the nitrogen. So instead of beta orientation, we adopted a para orientation of the two nitrogen units. In the difference density plots here, you can see that the HOMO and LUMO are alternating each other. So this TBISICG molecule has MR properties. And also in the emission spectrum, the emission spectrum was shifted from violet region to the blue region by changing the orientation of the nitrogen. Still, we can keep the multi-resonance character, and also we can shift the emission spectrum, and the FWHM was still small, and the stock shift was also small in this para-oriented molecule. In this kind of MR-TADF materials, actually we need to understand the RISC mechanism. And this year, site group reported that in the boron-based emitters, the main mechanism of the TADF is the second-order RISC by spin bibronic coupling. So S1 state of boron emitters is a shown range CT, and also the triplet state is also shown range CT. So the transition from T1 to S1 is forbidden. But because of a non-adiabatic coupling between high-lying T state, actually in the boron compound is a T3, not T2, but because of that coupling between high-lying T triplet state and T1 state, the non-adiabatic coupling is possible, and that second order RISC is enabled because of this bibronic coupling. So we can divide the spin-orbit coupling between S state and T state like this equation. So direct SOC can convert the triplet extons into singlet extons, and also spin bibronic coupling can also convert the triplet extons. But direct SOC is very weak, so the main process of the conversion in boron compound is a spin bibronic coupling. And that equation can be approximated as the equation below. And here we can notice that non-Born Oppenheimer process is very important between T1 and T2. Actually, in the boron, it's a T and T3 state, but anyway, that is important. And also, spin-orbit coupling between S1 and T2 state is also important for the TADF process. And also, one important thing is the difference between T1, T2 energy gap and also singlet triplet energy gap. If that is quite close, then there's a high probability of a conversion, and the RISC process can be activated. So in our molecular design, as I mentioned, we used two fused interlock Haber units. And in this figure, you can see that if we change the chemical structure of the building block, then TPA, PCG, ICG, then some planarization will happen. And if we fuse two interlock Haber units, then we can realize the MR structure both S1 and T1 state. This kind of planarization will accelerate the RISC process, because both the S1 and T1 will have a MR character. Without MR character, the delta EST will be quite large, but the MR character in S1 and T1 state can reduce the S1 and T1 energy gap and maybe facilitate the RISC process. And also in this molecular design, we added some substituent, and we used the T-butyl group or T-butyl modified panel unit. And T-butyl unit was introduced to control the homo level of the BIS-ICG material, and T-butyl modified panel unit was used to control the LUMO level, and also the T-butyl unit was used to have a blocking effect, because the core structure is completely planar, and then there will be strong intermolecular interaction without that blocking group. And also this kind of materials can be easily synthesized just by two-step reaction procedures, and we synthesized BIS-ICG, TBIS-ICG, and also TPBI-ICG. So firstly, we calculated the delta EST and delta ETT of the TADF materials we synthesized. So if we use a fused structure and the gap, the difference between delta EST and delta ETT is decreased, and especially the final target molecule, TPBIS-ICG, actually shows almost the same delta EST and delta ETT. Maybe this molecule can be promising as the TADF emitters which can utilize the spin bibaronic coupling procedure for triplet conversion. In this table, you can see that the delta EST and delta TT difference is only 6 millielectron volt if you use TP BIS ICZ molecule, and the SOC is not that different in these three molecules. Oh, okay, just a moment. Also here, we have to confirm the non-adiabatic coupling between T1 and T2 state. If you see the particle distribution, then the S1, T1, and T2 are almost the same. But in the whole distribution, the T1 and T2 show different whole distribution, indicating that vibrational coupling between these two states through non-adiabatic coupling can be possible because the origin is different. And also in the simulation, the RISC rate constant is high when we have a small difference between delta ETT. So this, for vibrational coupling, we need some vibrational mode between T1 and T2, and we calculated the vibrational mode of this molecule. And here in C, in the last figure of C, the vibrational energy of the phenyl central ring is around 1500 wave number, so that corresponds to around 0.2 electron volt. So that 0.2 electron volt is the energy difference between T1 and T2 state, and also delta EST of that molecule. So the resonance can happen because of this vibrational motion of the molecule, and that motion will turn on that RISC process. So in the case of BISICZ, the delta EST is larger than delta ETT, then in this case, the RISC process is prohibited. But in the second case, if you use TP BISICZ, then the RISC process is possible, then we can realize TADF emission from this molecule. So this is the mechanism of the spin bibaronic coupling based TADF. So T1 to S1 transition is basically forbidden because of L-side rule, but the non-adiabatic vibrational coupling between T1 and T2 can enable the RISC process. And the SOC matrix element, of course, important, and S1, T2 SOC matrix element was large in this case, and this is also important for the RISC of this TADF molecule. And of course, as I mentioned, the small gap between delta EST and delta ETT is very important, and the T1 to S1 procedure will be enabled through the T2 state through spin bibaronic coupling. And this is the data of the TADF materials, and here you can see that the stock shift is around 10 to 15 nanometer, and the FWHM of these materials is around 22 to 27 nanometer. So these TADF emitters showed very narrow emission spectrum and also very small Stokes shift, but the delta EST was not that small. And when we measure the transient pair, we could detect the delayed fluorescence from TBIS-ICZ and TPBIS-ICZ. So only two materials showed TADF emission, and the PLQI of these two materials was over 90%. But the problem in this molecule is the relatively long delayed fluorescence lifetime. So the delayed fluorescence lifetime was in the millisecond range, and the KRIC rate was relatively low because of that long delayed fluorescence lifetime. And we confirmed the TADF properties by temperature-dependent transient pair like this. And we fabricated devices using these emitters. And as I explained in the material design concept, the tertiary butyl substitution shifted the HOMO level, and the T-butyl modified panel substitution shifted the LUMO level like this. And the TADF devices actually showed a high efficiency, especially the TP-BIS-ICG molecule showed a high external quantum efficiency of 23.1%, and in particular, the color coordinate of this device was 0.15 and 0.05. FWHM was 21 nanometer, and the peak wavelength of this material was 452. So I think this peak wavelength is ideal as the deep blue emitter for OLED application. And this molecule showed a high EQE because of a high PLQI and also horizontal dipole orientation. So the TP-BIS-ICG molecule showed a high horizontal dipole orientation ratio of 90%, and this is one reason for the high EQE of this TP-BIS-ICG molecule. And also we confirmed that delayed fluorescence component from transient EL analysis, and especially the TP-BIS-ICG molecule showed clear delayed fluorescence even in the EL devices. So this figure shows the device performances of phosphorescence and DA-type TADF materials and boron-based MRTADF materials. And the device performances we achieved in this work is one of the best one, especially when considering the Y color coordinate of the emitters. Okay, this is the conclusion of my presentation. Actually, we developed MR-type TADF materials based on purely carbon and nitrogen without any boron atom, and this kind of molecular design could convert triplet extons into singlet extons by spin vibronic coupling based second order RAC mechanism. Of course, still we have to solve several issues in these molecules, but this kind of approach can be useful when we develop pure blue emitters for next generation OLEDs. Okay, this is the end of my presentation, and I would like to express my special thanks to SITE, and this work was a collaboration between our lab and SITE. Thank you. Okay, we will have some questions from invited speakers.
JY, I'd like to ask a question. Thanks very much for your talk.
Okay.
On slide number 24,
okay,
if you could go back to that.
Yes.
Yeah, that's a really odd-looking quantum efficiency roll-off. Do you have an explanation for that?
Yeah, so the problem of this kind of molecule is the serious efficiency roll-off at this moment. So as you can see in the photophysical data, actually the delayed fluorescence lifetime was too long. It is in the millisecond range still. So because of that, the maybe triplet extern related quenching processes will be very active, and maybe that is the main reason for the serious efficiency roll-off in these devices. Of course, that is the key point, and then we have to challenge the long delayed fluorescence lifetime issue of this molecule.
Do you have an explanation of why it looks like there are 3 regions for the roll-off. There's sort of the usual flat region, then it goes down at a certain rate, and then it goes at an even faster rate at about 10 milliamps.
Okay, I think this is a kind of log scale data. So I think that's one reason. But I think in the last like region 1, region 2, region 3, I think in this case the device was not very stable because the host materials we used is a really high triple energy host material with very poor stability, and the efficiency drop in the region 3 maybe due to the instability of the materials, and in the initial region the efficiency is high because of less catching mechanisms, but in the second region I think maybe mostly TTA based catching processes may dominate the efficiency of the devices.
Thank you. I'm sort of fascinated that today everybody has spent all their time talking about the luminescent molecule, the chromophore, but nobody has talked about the stability of the hosts. Maybe a topic for the next workshop.
Okay, yeah. Good suggestion. Okay, any other questions? Okay, I think... oh, yeah.
Oh, sorry. Can I have a question?
Oh, yeah.
Thank you. So thank you very much for your very interesting talk. And I have a question about equation of spin binomial coupling.
Okay.
Actually, I think that this is slightly different from the previous one reported by Professor Penfold and Monkman.
Oh yeah, originally they reported, and then after that the site people reported this approach.
Yes. And the difference is in the this parenthesis.
Okay.
That you have two items.
Yes, spin binomial coupling, you mean?
Yes, spin binomial coupling, and in the parenthesis, you have two items.
Yes.
One is energy depending on the energy difference of triplet 2 and triplet 1, and another is energy difference of triplet 2 and singlet 1.
Yeah, right.
Right?
Yeah.
Previously it was divided in the different, but now it's in the one term, one equation, one parenthesis. So that means if you have, as long as you have a very small energy splitting between the S1 and the T2, you don't care about energy splitting between the T2 and the T1.
No, that is also important. T1 and T2 gap. Yeah. T1 and T2 gap is also important, and especially that vibrational energy. For vibronic coupling, actually the energy difference between T1 and T2 should be matched with the S1 and T1 energy gap. So that is an important parameter.
Oh, really?
Yeah.
In this parenthesis, if one item is very large, another is not so important, right?
Oh, yeah. That's right.
But in maybe there is other factor. Maybe I see. So anyway, this is very interesting for me.
I think you can check the references here because they they reported detailed procedures using your borrowed materials.
Yes.
Yeah. So you can check that reference.
Okay. Thank you very much.
Okay. Thank you. Yeah. Okay. I think several questions from the audience. I think one audience asked about non-adiabatic coupling. Actually, it is a calculated result, not the experimental result. So it was actually detailed information about the calculation is in the paper here. So you can check that reference. I think there's some other questions, but I think because of time limit, actually, I think I'm sorry, but I cannot handle all the questions from the audiences. And I think this is the end of this symposium, and especially I would like to express my special thanks to 7 invited speakers today. Actually, we had a really fruitful discussion, and also we could set up the direction for the development of high efficiency and highly pure and long-living OLED devices. And I also would like to thank all the participants in this symposium. Of course, it was an online symposium, but actually there have been many questions from the audiences, and I think we really enjoyed this symposium with many audiences on YouTube. And thanks again for all the guests and speakers for joining this symposium today. Maybe, hopefully, I can host another symposium next year with different topics about OLED. Thank you again.